Good afternoon, everyone. Welcome back for the afternoon session, again with invited talks about various topics. And this morning, the session was very interactive with lots of questions from the audience, which is great. So let's continue this good vibe and let's continue this high level of interactivity. So the first talk of the afternoon session is actually a joint talk given by two speakers. The first speaker is Jana Shaban from Heidelberg Instruments Nano, Switzerland, and she will be talking about thermal scanning probe lithography for advanced photonics devices. And then right after her talk, Sven Proos will start his presentation. He's also from Heidelberg Instruments from the Germany department, and he will be talking about laser lithography for photonic applications. So after both speakers have finished their presentation, there will be again time for questions. So if you have a question, please don't hesitate to post them in the Q&A box. Okay, Jana, the floor is yours.
Hello, everyone. Thank you for joining me today. So I work as an applications engineer for Heidelberg Instruments Nano, and today I will be talking about our NanoFraser technology, which is a thermal scanning probe lithography technique, and I will detail how we can use this technology to create advanced nano devices and also devices relevant for the photonics community. So I'll start by giving an overview of our NanoFraser patterning technique, and then I will talk about the different pattern transfer possibilities that we use in combination with this method. And I'll also detail the different unique applications and features that our technology enables. So when can we use the NanoFraser? We can use it whenever we need to artificially make nanostructures on the surface. And the key concept here is to use a heatable cantilever tip for nano patterning features on a thermally responsive resist. So whenever this cantilever tip touches the surface, the resist is immediately sublimated, and this happens on a microsecond scale. And the reaction in this case is also endothermic, so it does not heat up the substrate, and it's also non-invasive. And we can use such a technique to write nanometer resolution features. And in this case, the tip shape itself, which you see here, gives the final resolution limit. And in our case, because we employ ultra-sharp silicon tips, this is the equivalent of about 10 nanometer resolution in the lateral direction and about 1 nanometer in the vertical direction. And what's very important here as well is that we don't have any need to correct, or no proximity corrections are required. And what's also very important for the NanoFraser principle is that we actually combine the writing with the reading, and this is done all in situ using the same cantilever tips illustrated here. So actually, in addition to an integrated microheater, which you see glowing up in this picture, we also have an integrator topography sensor on the same cantilever tip, which is used to image the patterned samples. And we also have an integrated actuation that can very accurately move this cantilever tip up and down. And we combine these reading and writing capabilities to perform so-called closed loop lithography patterning. So in this case, you can see it illustrated in this video here. Right. So while actuating the microheater of the cantilever with a hot tip moves in one direction and removes the resist according to your input design. And then switching off the tip heater, the tip goes back to room temperature in a matter of microseconds. And then it can be operated as a standard AFM to image the topography that was previously patterned. And by doing so, our software actually compares the deviations from the intended design and feeds it back to the next line of the pattern. And in this way, any slightest design deviations of even a single nanometer can be corrected and adapted into the next line to be patterned. So this is a very powerful combination because we can see exactly what we're getting as a final design. So it's really what you see is what you get type of patterning. But in the end, we don't just want to pattern shallow features in resist. We also want to transfer these high resolution features to functional materials in order to fabricate nano devices. So I'll go over the different pattern transfer techniques that we can use in combination with this patterning method. And actually the simplest one is using a bilayer liftoff, which I'm sure many of you are familiar with. So in this case, we just spin coat our thermally responsive resist on top of another liftoff resist. And we go on with the patterning as usual on this PPA thermally responsive resist. And then in the next step, we do a wet etch process to create this undercut here. And in doing so, we can deposit metals or dielectrics, any type of layers using, of course, a directional deposition method. And then by removing this liftoff resist, we get our final intended design. So this is quite a simple pattern transfer method, and it's suitable also for simple, smaller labs because it only requires wet etch chemicals in this case. And in doing so, we can reproducibly achieve patterns that are about 100 nanometer in size. And we can also, depending on design, achieve smaller feature sizes as well. But in this case, the feature density is limited. So if we were to transfer higher resolution and also more complex or arbitrary shapes, we need to modify this resist stack a little bit. And this is what we do in our high resolution liftoff method. So in this case, below the PPA layer, we use a spin coatable or even an evaporated thin hard mask. And we use this then to transfer the material onto the liftoff resist. And the reason here the PPA is so thin is because this is also what affects the resolution of our features. Because as I mentioned earlier, actually the conical shape of our nanofraser tip is what defines the resolution. So you could see that the deeper you go into the PPA resist, the larger the features become. So it's important in this case to keep this as thin as possible. And in doing so, we can carry on with our liftoff process. And you can see how much finer features are then readily patterned. We can use this technique to lift off different material systems. In this case, I show an example of plasmonic antenna, which were produced using this pattern transfer technique by lifting off gold. It's also possible to lift off the electrics, as you see here. And it's also possible to perform this liftoff on top of pre-existing topographies. So I'll come back to this idea a bit later. Now, if we wanted to transfer these patterns to the layers underneath and etch them down, actually, we use a third technique, which is 2D high-resolution etching. And in this case, we can use the same material system. So it's essentially a transfer stack and just etch it down into the functional material of choice. And given the limited time, I won't go too much in detail into these different transfer techniques, but I invite you to watch our webinars online, which go into detail into each transfer process. So with this 2D high resolution etch, we can achieve very high resolution features. Here you see an example of patterns transferred onto silicon with 14 nanometer half pitch. It's also possible to transfer onto gold, and we can also achieve nice high aspect ratio features here. And also some repeated patterns of holes, also possible. And one example that we have been focusing on recently is also using the same high resolution transfer etch. We can create larger area silicon waveguides. So I show an example of this here. In this first image, you see how the design is patterned onto the thermally resistive PPA layer. This is actually an image taken from the NanoFraser software tool itself. And below you see how it nicely transferred onto the silicon after etching. You can see an AFM image of it and also an SCM. And this shows that our initial feature sizes are nicely reproduced in silicon. And of course here the edge roughness can be smoothened out if we use smaller pixel sizes in our initial design. So all of this can be tuned. Another thing we can do with our nanofraser technology, other than 2D transfers of patterns, we can also do multiple profile depth or so-called grayscale lithography transfer. And this is shown here. So in this case, we can also just use one thick layer of this thermally responsive resist PPA. And with our cantilever tip, we can go as deep as 250 nanometers. And we can very accurately tune the depth profile here and transfer it with a dry etching step into the material of choice. So one prominent example is transferring such a pattern into silicon. So if we were to talk about a PPA and silicon substrate in this case, we have to keep in mind that the selectivity of PPA against silicon in etching is about 10 at maximum. So using this 250 nanometer layer of PPA, we would get a depth in silicon which is on the order of a few micrometers. If we want to amplify this etch depth even more, we can of course then simply add a hard mask layer underneath the PPA, and then we could virtually amplify this depth however much we want, depending on the hard mask layer introduced. So using this 3D etch transfer technique, we could create nice 3D holograms in silicon. So what's cool here is that you can see the input design that we gave our NanoFraser software. You can see 8 discriminated levels of grayscale to pattern. And you can see exactly how they transferred into the PPA resist. And what's nice here is the very accurate control of the depth that we could achieve in this profile. And also we could reproduce it in the etched final silicon device as well. And here we were able to amplify this depth by over 10 times. So using the same 3D transfer, there are many other cool examples that have been published in recent years. And what's interesting to note is that our NanoFraser technology opened room for new devices that were not possible to pattern previously, or at least not with so much ease. And I give example to this optical Fourier surfaces that Prof. Norris explained yesterday, and also other applications relevant to you, like photonic molecules and also faceplates and different materials. Another really nice feature is the fact that we can detect and read using our tip in C2 AFM mode. We can detect existing topographies, and this includes things as thin as 1D material like nanowires, or even 2D materials like MOS2 flakes and graphene. And what's noteworthy here is that we don't actually need any markers to be left on the sample. So what we simply do is go to the area of interest, image the sample. So of course we can detect these topographies even under our resist stack. So we can image it and then simply overlay using our software, overlay the desired design on top of the already imaged AFM picture. And you can see an example of this here. So here is the image of that we get using the cantilever tip in reading mode. And you can see how we can very accurately overlay this gate electrodes on top of it. And this is the final result after the pattern transfer and liftoff. So far I've talked about our capabilities using the cantilever tip. If we want to increase throughput, we also can use a special laser add-on that we have integrated to our tool. So using the same material system described earlier, we can also use an integrated direct laser sublimation system. And this is used to pattern larger areas, so say on the micrometer scale. And you see a nice example of this here. So on the same material system, same sample, we can write these large micrometer features with the direct laser sublimator. And this, of course, just sublimates the PPA directly, so there's no need for subsequent development or wet chemistry steps. And then using the cantilever tip in the heated mode, we can write the same type of logo, but on a much smaller nanometer scale. And then using the same cantilever tip, but in the cold reading mode, we can image this entire area here. And I can show an example of how all of these technologies were used in combination to create a single electron transistor. So here you see some pre-existing patterns, which are on the many micron scales. I think they were done with photolithography. And if I zoom in into this green area here, you can see how we were able to overlay our design and write it with the laser very accurately to the existing features. And then zooming in even closer to define the finer features here in blue, we use our cantilever tip to design nanometric size features here. And you can see in the overall picture how they're all very nicely connected and overlaid one to the other. And to increase throughput even further, we are currently working on a commercial tip array holder. So we've already demonstrated the functionality of a linear 10-tip array already, and we're planning on rolling this out commercially for 2022. So very exciting things coming up. And with this, I'd like to end my presentation. I hope I was able to give you a good overview of our nanofraser technology and the different applications it enables. So I look forward to your questions at the end of Spen's presentation. Thank you. So I'll stop sharing now.
So can you see the screen? Okay. So yeah, so I'd like to continue following this presentation with some news about laser lithography for photonic applications. And you might know that in addition to the nanofraser tools that we just learned about, we offer a range of different laser-based systems for direct writing. And there's basically three categories that we have. It's the MLA or maskless aligner systems that are basically used as a replacement for mask aligners and offer more or less the same capabilities. Then we have the VPG Plus and Ultra systems, which are tools that are used for photomask production. And then we have the DWL tools, which I will talk a bit more about now. These are mainly used for grayscale exposures, but generally they're very flexible tools, offer a lot of options, and they offer some great capabilities for photonic applications. The DWL systems, like all of our tools, use spatial light modulators to control the light intensity. And this device basically receives the data from a CAD file and converts it into the image that we want to expose on the substrate. The image is focused onto the substrate. In this case, it's a line of pixels, and the stage system moves the substrate underneath this focused image. And we raster scan the entire surface of the substrate. It has the big advantage that the quality and fidelity of the structures is very high, the position accuracy is very good, and the write time does not depend on the number or shape of structures. Basically depends only on the overall area and the resist properties of the substrate. The spatial light modulator that we use in the DWL systems have the advantage that they're very fast, and they offer the possibility to modulate the intensity of each pixels with up to 1000 levels. So for grayscale exposures, which is the main application for this tool, it offers very good capabilities. But also the systems offer the highest resolution that we can offer, down to 300 nanometers. And it is possible to expose these high resolution features and also this grayscale features on substrates as big as 1.4 meters. That's the theoretical limit. In the field, we have a number of systems that go up to 800 millimeters, but in theory, we can do 1400 millimeters. It's also possible to expose non-flat substrates. I will tell you about this a little bit later. When we look at the resolution, as I said, we specify 300 nanometers, but if you just write simple letters like these lines, you can even go a little bit below this. So this is something like 250 nanometers that we achieved in a standard 300 nanometer thin resist. If you go to more realistic patterns, this is the example of a spiral waveguide. You can see that we also get close to these 300 nanometers. Also, the uniformity is very good. And the lines are also very smooth, as you can see. So this was also written in raster scan mode. So it's a pixelated image that we write. It's not like we have a single laser beam that's simply writing this one line. It's really made up of pixels, and the uniformity and the line width is still very nice. This is another example of a coupled waveguide, also a few microns across. You can see here that it's also in the range of 300 nanometers, very uniform. And you can also see that it's possible, even possible to achieve slightly smaller structures in this resist feature that remains basically between two lines that we wrote with this system. So it's even possible to go below the 300 nanometers in some cases if the process is stable. And this kind of resolution, you would usually need either a stepper and a high resolution photomask or an E-beam writer to achieve this. And this laser system offers a much faster and easier way to achieve this resolution. The other main application of the DWL systems is the grayscale lithography, as I mentioned. In this mode, we basically modify or modulate the intensity of the pixels while moving across the substrate. So for each pixel, we can control the intensity and define how deep the resist will be exposed. And when you do the development of the resist, the features will appear according to the intensity that you apply to each pixel. This mold in the photoresist can then be transferred into the substrate by etching, or you can use it as a master and do electroforming, or use something like almost stamp to create a negative that you can use for further processes. The data that you can use to create these images can be supplied in different formats. One very common format is the DXF. In this case, you would have a DXF file with up to 1000 layers, and each layer would represent one intensity. So you can create your image this way. Another possibility is a native 3D format like the STL file. You directly supply a 3D file, and the software will automatically cut this into layers and assign gray values to each pixel according to the Z value of this STL file. Third possibility is just an image file, a bitmap, JPEG, something like this, with gray values, and the gray value will define the intensity for each pixel. And the last one is an XYZ file, just an ASCII file with coordinates. This can be very convenient if your structure can be defined by an algorithm, for example. You can directly, with the algorithm, create this file and then use it by the software to create the image. The software is also quite powerful and allows you to use all of these file formats, combine them into one big design. You can merge different files, combine 2D and 3D designs, and create very quickly large areas, very complex grayscale designs that can be exposed. So this is an example of things that we do. One is, of course, microlens array. So if you want to expose an array like this, you only need to create one lens as a design, and our software will automatically step and repeat this. You can provide the raster and then expose it very quickly. Microlens arrays are, of course, used for various applications, beam shaping, glide homogenization, these kind of things. Second application is the Fresnel lenses, can be up to several millimeters or even centimeters if you like. Also very easy to supply the data for these Fresnel lenses. Also very popular is the diffractive optical element, used to modify phase profiles of the light, used for security markings, holograms, all of these things. Then another application is the exposure for diffusers and reflectors, also used in display applications, for example. Then you can do blazed gratings for spectrometers or similar applications. And there are always new applications emerging that people use the grayscale exposures for. You can texture surfaces, for example. We have some people who use it for medical applications to create certain surface textures. For MEMS, it's sometimes used, and also for some other things. The quality of the structure is, of course, depends on the system, but the system is generally very reliable and provides very good uniformity across the exposure. The process itself, the development and the resist coating is also very important. This is an example of what can be achieved if everything works together well and the process is tuned well. These are lenses with a thickness of about 25 micron, and we achieved in this case surface roughness across the lenses of less than 5 nanometer RMS. That's without any treatment. It's simply exposed and developed, so there's no reflow or anything. So this is what's possible if everything works well. Most of the grayscale applications work in the resist thickness range of maybe up to 20 or 30 micron, but there's always some applications that would like to go thicker, like in this case, we exposed some pyramids in 56 micron thick AZ4562. And that's pretty much the limit of the thickness that can be exposed so far. The thicker the resist, the more difficult it is to get uniform resist slopes, and also the process is more demanding. However, we are always working to improve things, and this is a very new example of something that we're testing right now. Together with a manufacturer of photoresists, we try to find a resist that can expose to depths of up to 100 micron or possibly more. So this is a very first test result. The resist was coated to about a 140 micron thickness, and we exposed the slope that's not fully optimized. So it's basically a first test, but you can see that we already have a usable range of about 100 micron in this case. And this was the first test of an oval lens that we did. It's also quite promising. So that's something we're working on at the moment. And we know there's quite a number of people interested in this kind of thickness. Another advantage of this maskless exposure technology is that it's a non-contact exposure process. So when you have a substrate that's not completely flat, if you use a photomask, you have the problem that across the photomask, the distance between the photomask and the substrate will vary. And this will translate into the patterns that you're exposing. So varying distance will change the width and the uniformity of the patterns, and it's very difficult to achieve good exposure quality across a substrate that's not uniform. The advantage of the maskless exposure is that it's a non-contact, and we constantly track the distance to the substrate. And during an exposure, we have a dynamic range of 150 micron, in which we can follow the surface, and the system has a static range of even up to 10 millimeters to do the exposures. And with this, you can expose on substrates that are even have different levels, which is nicely illustrated in this example from the Fraunhofer. They had a wafer with etched trenches that were 500 micron deep, and they wanted to expose on the slopes of these 500 micron deep trenches. And this is the first attempt they tried with a photomask. And as you would expect, on the top surface, everything looks nice. But the further you go away from the photomask, the line width changes, and the pattern down here is not what you want it to be. With a direct write system without contact, they managed to write these very uniform structures on the sidewall, and they even exposed their logo and etched it in or created it in gold to show what they can do. You can do this even with thicker substrate. So in this case, you can use substrates up to 10 millimeter in height variation, and this will allow you to expose, for example, on concave substrates to create features on this concave mirror, for example. Or you can even write high-resolution features or micro lenses on these macroscopic lenses and combine microscopic and macroscopic optical elements. So to summarize how the maskless lithography can be used for photonic applications, basically it offers the possibility to expose high-resolution features that would otherwise require either E-beam or a high-resolution mask and a stepper. You can fabricate with grayscale arbitrary topologies, and you can even do this on non-flat substrates up to 10 millimeter thickness. Yeah, with this, I'd like to thank you, and if there's any questions.
Thank you very much, Jana and Sven, for these very detailed and interesting talks. Clearly, lots of opportunities, flexibility, and advantages in both techniques that you presented. We have time for questions. Perhaps I can start with the first question. Well, I have a question for both Jana and Sven. So Jana, you just out of curiosity, you mentioned that the scanning probe can go from heated status to room temperature status in microsecond timescales. I was just wondering, is there a specific technology that you use for making this fast temperature transition possible?
We have an integrated micro heater on the cantilever tip itself, but I actually would not know the nature of the micro heater itself. But I'm sure there are webinars that you can refer to for this, or maybe Anya has more detail about that.
It's just a resistive heater. It's just
okay. No special.
No, it's just yeah, I think the whole cantilever is made of silicon.
Yeah.
And there is some material modification local that creates the resistance. Okay. I don't remember offhand which one it is.
Okay. I also have a temperature-related question for Sven. So you're using laser lithography and you focus the laser beams. What about thermal effects in your substrate? Is that a concern, or is that something that you need to take into account when designing your pattern, for example?
No, that's nothing you need to take into account. We were basically exposing the photoresist like you would do with a mask aligner. So we are supplying basically the same amount of energy. We just do it very fast. So the laser pulses that we use are in the nanosecond, or depending on the system, microsecond range. But the powers that we use for the exposure, they create no heating effects. We also have tested this for some customers that had the same concerns because they were working on sensors where the material would be sensitive to these possible heat changes. And there was no effect, basically. It is, of course, possible with the laser to increase the power to a level where you can damage the resist or even the substrate. You can burn it if you want to, but for standard exposure, there's no thermal problem.
Okay, thank you. Any other questions? Yes, Tata, go ahead.
Yeah, thanks a lot for these very nice presentations. And my question is for Sven. So you mentioned that once you simulate one micro lens, then the program, it does like automatically the full array. So how long it takes to build, because you have shown 200 micron range, right? If I'm not mistaken. So how long it takes from one micro lens to reproduce like within 200 micron range, and how much is the reproducibility? Is it like perfect reproducible, or there are like tolerances?
So if you're referring to the data, so if we create the data, like I said, you can make a single lens and then step it or rotate it or place it in different ways. That's done very quickly within the software. It just copies it basically. So that's creating the design itself does usually not take very long. If you then afterwards convert this design to a machine readable format, then this let's say vector-based design that we have converted to a pixel-based design, that can take some time. It depends, of course, on the area and on the complexity of the design. It can take from a few seconds to honestly a few hours. We have customers that, like I said, that expose to 800 by 800 millimeters, and that can create terabytes of data that you have to process, and that will take some time, of course. But you have the choice if you want to create the design before the actual exposure, or if you know it's going to be quick, you can start the exposure and the system will create the design right away. In terms of reproducibility, the data itself and the exposure process is very reproducible. There's also some tricks that you can do with the lenses, for example, to change the width of the lenses slightly to match them to the properties of the system, to the grid, for example, and that can make it very reproducible. But if you go to large areas, and I'm talking about maybe 10 by 10 centimeters or something bigger, then the process is more the limiting factor. To have a uniform development process across large areas, that creates bigger problems than the exposure itself.
Okay, thank you. So if there is time, I have another question.
Yes, go ahead.
Thank you. Yes, so my question was related to the moving of the beam while doing the direct writing, how it affects on the quality of printed devices, like from one spot to another spot when it moves. Also, this question can be for Jana.
Jana, you want to go first?
So actually, this in our case would depend on the accuracy of the piezo stage, which is moving underneath the beam, and we don't have. I mean, it also depends on the pixel size you're using in your initial design. So if you're using smaller pixel sizes, you'll get more smooth transitions. If it's larger, you might get more rough edges, but otherwise it works quite nicely.
Do you have any limitation, like a lower limitation for the pixel size, so don't go smaller than these? And then there is a trade-off between the resolution and the pixel size, right? If I'm not mistaken.
It would be a trade-off between the pixel size resolution and also with the speed of patterning. So the smaller the pixel size, the longer it takes. But also going back to your initial question, so for us, for the NanoFraser, the field that we pattern is 50 by 50 micrometers. And if you want to pattern larger areas, then you need to stitch 50 by 50 micrometer fields. But actually, we have an integrated algorithm for that, for the stitching. And in this case, we use the AFM mode to pattern the existing patterned field. and stitch it to the next field that we would like to pattern. And so we can do that with an error of less than 50 nanometers.
Thanks a lot.
So for the laser, maybe I can add, it's a little bit different because the NanofRASER uses a much more accurate stage system and uses this step and repeat process that Jana just described. For the laser systems, we scan on the fly. So we move the stage with quite high speeds underneath the laser beam. But the quality is still very good. For one thing, we have a large overlap in individual pixels. Like you saw in the image of the waveguide, it's made up of individual pixels, but the overlap is so high that you get smooth lines.
Right.
Also, we have a feedback loop between the stage and the optical system. So while we move the stage at a constant speed, we measure with interferometers the position, and we constantly feedback this position information into the optics system. And then in the optics, we have the possibility to very quickly adjust small changes that are created by the mechanics of the stage. And this way we achieve also accuracies in the high-end system in the range of a few nanometers.
Okay, thank you very much.
Good. So thanks, speaker, again. And I think we can move on to the next talk, which will be a talk given by Shane Itzene of IFNCNR in Italy. And the title of his talk will be Laser Writing of Color Centers and Optofluidics in Synthetic Diamond for Quantum Sensing. So once again, to the audience, if you have questions, just post them in the Q&A box. And Shane, the floor is yours.
Thank you so much for this invitation, Natalie. This is actually my first ever talk during the pandemic, so I'm a little bit nervous, so my apologies in advance, but I'm very excited to present our research on laser writing of quantum technologies within diamond. So this is following up on the lovely talk we just saw. So another application for laser fabrication. In this case, we're looking at making diamond-based quantum technologies. So my name is Shane, and I'm with the IFN, which is the Institute for Photonics and Nanotechnologies at the National Research Council here in Milano, Italy. So I want to first acknowledge my great research group. Of course, without these young guys, and this work would not be possible. My supervisor is Roberto Ramponi. She's the director of the Institute for Photonics and Nanotechnologies. We also work closely with Ottavia, who's based in Como, Lakeside. This picture was actually taken in South Africa for a different collaboration. Here is Lebo in the middle. He's a researcher in Cape Town. My star PhD student, Argiro, and I'll present some of her research later. And then me, of course, on the right. This shows our laser fabrication lab in Lecco. So I'm actually currently in Milano, but we have a second lab in Lecco nearby. And here we see my postdoc, Vibha Bharadwaj. Poor guy's been stuck in India the past year and a half because of the pandemic. He went there to get married, and he hasn't been able to come back, unfortunately, but we're expecting him here in the next days, maximum weeks. And so excited to have him back. We have my master's student, Paola, and our brand new PhD student, Giulio. And we have very important collaborations around Europe and the world. I have to thank specifically Paul Barkley on the left, who is basically inspired me to first explore this application within diamond using laser microfabrication. And our first experiments were done along with his postdoc at the time, JP Haddon, who's now based in Cardiff. And we now have a European project together with JP, in addition to Alexander Kubanek of Ulm, and Paolo Oliveira of Torino, and also Angelo Biffone of Torino. So to give you guys a background on quantum information, the quantum world, I'd like to give this example, which was taken from Michelle Simmons' TED Talk several years ago. And so what she proposes, imagine you're at the center of a sphere, for example, the planet Earth. So of course, in the classical world, you can be in the 0 or 1 state of digital information. So of course, if you're pointing up towards the North Pole, that's your 1 of digital information. If you're pointing down towards the South Pole, that's your 0 of digital information. Now, of course, in the quantum world, you can be pointing anywhere on the surface of the sphere. You can be pointing towards Milano, for example. You can be pointing towards Cape Town. And as a result, you're in a superposition of states, partly up, partly down, just like the wave function of an electron. The advantage, of course, of quantum computers is they can check for many possibilities in parallel, unlike modern classical computers, which work in series. in rapid succession. And this has many exciting applications in very, very complicated problems in modern science. The question is, how do you realize a quantum bit? Researchers have proposed using laser-cooled ions, but one very promising quantum bit was discovered in a solid-state system, specifically diamond. Whether it's synthetic or naturally found diamond, there are defects within this nice regular carbon lattice, of course, which give also rise to different colors of diamond. One specific defect is very exciting, where you have two adjacent spots in the lattice, modified with a nitrogen and also an empty space adjacent to it. And in an empty space, you have an extra electron whose spin can be controlled with light. And this allows us to do quantum information, but also quantum sensing. So I want to emphasize this is present, these defects are already there. They're present in both natural and both synthetic diamonds. Synthetic diamond is what I use for my research. So the NV center, this nitrogen vacancy center, this quantum bit in diamond is essentially like an artificial atom. It has great advantages such as long coherence time. It also can be operated at room temperature. Here shows a very simplified version of the electronic energy levels. The key point here is the excitation is in the visible around the green wavelength, and the emission, the zero phonon line is at 637, so in the red. And the great thing is these NV defects, these spins at the NV center can be initialized, manipulated, and all read out with light, with photons. And so a photonic technology would be very, very convenient in addressing these quantum bits. So in addition to being able to realize quantum bits for quantum information, for quantum computing, they also make great quantum sensors, because the ground state triplet is sensitive to magnetic fields, but also electric fields. And this allows for a nanoscale, extremely sensitive electromagnetic field sensor. So to give you an idea of how we could build up a quantum computer, this is a generalized scheme known as the quantum internet. And essentially what you have is our quantum nodes separated by quantum channels. And the quantum nodes, of course, would be these quantum bits, these NV centers within diamond. And what I propose is to use laser writing to form communication channels. So essentially these quantum bits can all talk to each other in this three-dimensional configuration. And this is what's known as long-range entanglement. Now, quantum computing, as many, I think, of you guys know, can solve these very, very complex multivariable problems in modern science. They're ideally suited to nanoscale simulations in modern chemistry and physics, but they can even be used in the future for macroscale problems, such as predicting the world climate or fluctuations in the stock market. Now, so I hope I've given you a motivation for why we want to use diamond photonics for both quantum computing and quantum sensing. Here is a picture taken from the Element 6 website. Most of my friends are a bit disappointed when I show them this slide, because they expect I'm working these beautiful gemstones, that you imagine you have on a ring. But these are actually just flat samples of synthetically made diamond, but usually by CVD, because it's much more convenient for us to work with flat samples instead of diamonds that have been cut to shine. It's much more easy to focus in with a laser and form our devices. The difficulty of diamond is it has many extraordinary properties. It has record high hardness. Of course, it has great transparency, but it's also very inert. And this makes it very difficult to do nanofabrication within diamond. And what I propose to use is laser fabrication to form these optical waveguides, so these communication channels between the quantum bits, but I'll even form the quantum bits themselves, these NV centers on demand. In addition to also microfluidics, which could be useful for quantum sensing. The question is, what kind of laser could be used for fabricating in diamond? And here, actually, this is a very nice picture taken from an MIT talk. And what it shows is essentially a laser incident, a blue laser, a laser in the UV, essentially, incident on basically inside a dial containing a fluorescent dye. And what you can see is that you have this focused Gaussian beam, which is coming in roughly in the blue. And you can see this green emission, this green fluorescence, because this is a fluorescent dye, wherever you have the focused Gaussian beam. It's a beautiful picture, but this means that we can't have very nice pinpoint 3D processing. We have absorption throughout the Gaussian beam, and so we can't have this precision three-dimensional nanofabrication using linear absorption. So here in this case, we're essentially using a very short wavelength of light to excite the electrons from the valence to the conduction band. This is much with the same case in glasses. Transparent glasses are also diamond. So what we propose to use are femtosecond laser pulses. And here we're typically using femtosecond lasers in the near infrared. Here's an example of a tie sapphire laser coming in again from the top, going through a focusing lens. And what you can see, in fact, here is a much more precise, it's very hard to see, but you can see this very precise green emission just at the focal volume, where you have an intensity over a certain threshold intensity to drive nonlinear absorption, as opposed to linear absorption on the left. So we rely on this multi-photon nonlinear absorption to achieve very pinpoint 3D microfabrication in transparent materials and also in diamond, for example. Here shows this is our laser setup in Lecco. The white box is our femtosecond fiber laser from Menlo, a company in Munich. And essentially, it's quite a simple setup. Essentially, it's various mirrors guiding our laser towards a final focusing lens. We have the options of using the 1030 nanometer fundamental wavelength, or we can even use the green wavelength, which is more compatible with oil immersion microscope objectives. And so that's typically what we're using. This shows the very final setup. And essentially, we have mirrors bringing it towards the final focusing lens. And we have our diamond sample, which we place on a three-dimensional computer-controlled motion stages, which are aerotech stages with very high precision. We also have the possibility to have real-time viewing of structures we fabricate using a CCD, inline CCD. Here shows the setup, here shows fabrication in process. What we can see is this. We have quite a bit of dust in the lab, so you can actually see, in fact, that we have, you can see the green line from the laser beam itself. One thing I want to point out here is, again, just like Sven's talk, we're maskless here, but we don't require a clean room. This can be operated in very, even with large temperature fluctuations in the lab, not the cleanest lab in the world. This is not so crucial for this direct light writing method. So a background on femtosecond laser fabrication. So this isn't a new concept. It's been around since 1996. The first group to discover it, former collaborators of mine, were from Kyoto, at the University of Kyoto, Davis and colleagues. And they were the first to show that by focusing femtosecond laser pulses beneath the surface of a transparent glass, the light was nonlinearly absorbed, resulting in a permanent refractive index increase, only within the focal volume. So if you then scan the sample relative to the fixed focus femtosecond laser beam, you can form optical waveguides, where you have a higher refractive index within the modification compared to the pristine glass. The advantage here, of course, compared to any other technique, is we can actually form these structures in 3D, which is quite compelling for photonics. So this work has actually been cited over 3,000 times already, mainly related to fabricating glasses, but also polymers, certain crystals. But up until my research, no one had ever addressed diamond. So to give you an idea of how waveguide writing can be done in crystalline diamond, so this shows an example of just waveguide writing on a typical glass. As I mentioned, you're forming this sort of cylinder of increased refractive index, which is responsible for guiding light. Here you can see a guided mode, which is known as type 1 waveguide writing. Now in crystals, unfortunately, as you absorb the light within the crystalline lattice, you're modifying the crystal. You're taking this nice periodic arrangement of atoms within the crystal lattice, and you're essentially modifying them. You're causing amorphization, which results in a decrease in density. And this decreased density results in a depression of the refractive index. So this is not ideal for forming with one shot an optical waveguide. And so what our idea is to closely space these two damage lines together to form a stress in between them. And through the stress optic effect, the idea is to form a positive refractive index change in this compressive stress zone between the two lines. And this is what's known as the type 2 modification. To give a quick idea of the diamonds we're working with, again, we're using synthetically made diamond. Here shows the lovely transmission window of diamond, which is great for even up to the terahertz. We're typically buying from either MD Optics or Element 6, two of the main sort of CVD diamond producers. Now, depending on the purity, you can go from low grade, which is made with actually a different process, high pressure, high temperature on the right, the sort of yellowish diamond, where you have a nitrogen impurity concentration of around 100 parts per million. And working your way up to higher purity and more costly samples, optical grade, which is typically what I use for my research, we have nitrogen concentrations of around 100 parts per billion. Whereas the high end, you have electronic grade, or what's known sometimes as quantum grade CVD diamond, and there you're looking at nitrogen impurity concentrations of around 1 part per billion. Now, depending on the application, whether you're looking for quantum information, you're typically looking at the most expensive diamond. If you're looking for quantum sensing, you're looking at a high concentration of NVs to boost sensitivity. You might be able to get away with HPHT diamond. The costs presently range from around €100 for HPHT up to €5,000 for electronic grade, depending on the size of the sample. So typically, the largest diamonds we can make synthetically are around, at this stage, 10 millimeters by 10 millimeters in area and roughly 500 microns in thickness. But these prices are always coming down. So our group was actually the first to demonstrate a laser-written waveguide in diamond. And essentially, as I mentioned, we wrote these two damage lines very within close proximity. This shows a microscope image with an overlaid mode profile. Essentially, the laser came in from the top to form this sort of elliptical damage line. And then we formed a second one adjacent to it, roughly 10 microns away. And of course, the sample was scanned out of the page to form this line throughout the sample. One thing to note here is it's quite elliptical due to the self-focusing within diamond. Even though we used an oil immersion lens, we had significant spherical aberration, my apologies, because of the high refractive index difference between the oil and the diamond, oil being around 1.5, diamond having a refractiveness of 2.4. This causes quite an elliptical modification within the diamond. But regardless, we found nice single mode guiding. Losses were reasonably low, around 4 dB per centimeter in the visible. One other thing to point out is that we had only TM guiding in the case of this waveguide. And here shows the various laser processing parameters, which may be of interest to some people. This was published back, I believe, in 2016 in Nature Scientific Reports. Now, we have these optical waveguides, which are great. We'd, of course, like to reduce their losses in the future. And of course, we have NV centers, as I mentioned, already present in synthetic or even naturally found diamond. But it would be much more convenient to place these NV centers on demand, perfectly aligned with the photonics we fabricate or even the microfluidics we fabricate for quantum technology devices. And actually a group, not my group, but a group was doing this research at the very same time I was, and unfortunately beat me to it. Salter's group, which is a friendly collaborative of ours now, first showed that by focusing a single femtosecond laser pulse, so typically we're using many pulses to form these optical waveguides in diamond. Here they're using a single and lower energy laser pulse to very gently modify the diamond. But essentially they're producing only vacancies, hundreds of vacancies within the focal volume of the diamond. They then apply a post-thermal treatment to cause these vacancies to then mobilize. And when they encounter one of these very rare nitrogen impurities within the diamond, again, you can design this so that you have the correct purity concentration you'd like to achieve single NV centers. They found that with a 50% success rate, they could achieve single NV, single photon sources with this technique. And we indeed showed at the very same time, they published their work, of course, in Nature Photonics. We showed a couple months later, a much similar result. Here we show on the top left, we show an overhead microscope picture of an array of the static exposures we formed. Now, these visible dots were essentially marker dots, so we could find this sort of invisible array because you can't see them by eye, you can't see them by microscope. So they were written with quite high pulse, laser pulse energies. But essentially what we found in this low pulse energy range, we could achieve single NV centers, again, with 50% success rate. Here on the bottom left, you can see the very typical photoluminescence spectrum from the NV center showing this nice peak at 637 nanometers. You see the confocal photoluminescence on the top right showing this nice emission. And also proving that we have a single photon source, we see the G2 going below 0.5. And so we're quite pleased that we could also fabricate in our labs this NV center on demand. Now that we have these building blocks to form both photonics and NV centers with the laser, we thought about combining the two. So I entirely made with the laser in the very same process step, we formed first this waveguide, and then we formed this static exposure in the middle of the waveguide, which we then annealed the entire sample. And thankfully, the waveguide properties were not degraded after this 1,000 degree thermal annealing. But in fact, we were able to form this single NV where in the static exposure in the middle of the waveguide, this single quantum bit. And so we showed the first ever coupled NV waveguide formed entirely with the laser. And that was done in collaboration with the University of Calgary. Another application, so that the application of single NVs are more compelling for quantum information. Next step would, of course, be to build up a three-dimensional, or let's say a three-dimensional network of interconnected quantum bits for quantum information. Another exciting application is quantum sensing. In this case, we want to work with a lower grade diamond sample made with HPHT. And the reason for that is because it has a higher concentration of nitrogen impurities, and therefore we expect to be able to form a higher concentration of NDs using this laser exposure. Sensing efficiency is proportional to the square root of the number of NV centers. And actually, this is where our initial very, very promising result. This shows an EM-CCD image of the NV emission from one of these waveguides. So this is taken from overhead from one of these type 2 waveguides. You see the two damage lines formed by the waveguide, formed by the laser. And in the middle, you see this very bright cloud, which we anticipated was due to these NV centers, due to the filtering we applied. You see that also on the right, where we have a nice filter, and we still see this nice streak of emission from the characteristic wavelength window of NVs. And so what we did is we actually performed quite a bit of analysis, and we show before and after the annealing. So of course, before the annealing, what we found is this situation here. So again, this is confocal fluorescence microscopy, a cross-sectional view. Again, you see these elliptical sidewalls making up the waveguide. And we see strong emission from the actual damage lines because we're forming quite a bit of defects within these sidewalls, okay? So they're actually NV centered, we're writing in the sidewalls. But what we really like for our quantum sensing application is this NV emission to come from the middle, where we have this overlap with the optical waveguide node. After annealing, after thermal annealing, it caused these vacancies that we produce within the sidewalls to mobilize. And what we found is a strong emission also within where we have overlap with the waveguide mode in between these two elliptical sidewalls. And so what we estimated is we could produce an NV concentration of 10 to the 15 inverse centimeter cubed. Our goal is to boost that by a factor of 100, which would give us the record high electric field sensitivity. We have several ideas on how we can do this through material property tuning, but also through fabricating static exposures, laser static exposures within the waveguide, within perfectly overlap with the optical waveguide mode. And so that's work that's ongoing with JP Haddon, who's now at Cardiff. This initial sort of preliminary work was published in this progress report in Advanced Quantum Technologies, along with JP Haddon. Another application we're interested in is microfluidics in diamond. You know, people think, again, a very expensive material to be doing microfluidics in when everyone's using PDMS. But of course, diamond has these great advantages of its inertness to biological and chemical materials, great transparency, and the fact that we can build this quantum sensor, this NV center adjacent to microfluidics, in order to sense flowing biomolecules. And so this is sort of the motivation for fabricating microfluidics in diamond. Now, as of yet, we've been unable to fabricate buried microfluidic channels in diamond. People have demonstrated this in glasses using the post-etching technique. But what we wanted to first show was surface microfluidics. And in fact, we showed very, very nice channels using these very standard focusing conditions here. And so we're quite pleased with the aspect ratio. And in addition, we combined this, since we need to actually combine this to microfluidic tubing external to the chip, we'd like to have through holes which are connected to microfluidic tubing. To form these through holes through the 500 micron thickness of diamond, we propose to use Bessel beams. This is work done in collaboration with Octavia and Como. And Bessel beams, compared to Gaussian beams, have the advantage of much longer, more elongated focus, which are ideal for forming these extremely high aspect ratio modifications. And in fact, we demonstrated through holes in diamond. This work was recently published, I think a couple of weeks ago, along with Octavia. And the idea is combining these two in a microfluidic chip, again, also with NV centers, and that's ongoing work we're doing with Avigito. Here we see the next step of combining the laser-written microchannel formed with Gaussian focusing, and then these through holes, which have the appropriate size for connecting with microfluidic tubing. You can see very nice SEM pictures of these microfluidics. So in summary, I hope I've convinced you that femtosecond laser writing is a very versatile tool. You can form not only optical waveguides. I demonstrated visible waveguides, but we've actually demonstrated in our group waveguides that work in the near infrared, up into the mid infrared, and possibly up to terahertz. We've demonstrated we can form both single NVs, which are useful for quantum information, and high density NVs, more useful for quantum sensing. And so the idea is working towards integrated photonics for NVs for both quantum information and sensing. Future work We'd like to, of course, in the case of quantum sensing, increase the number of NV centers to boost the efficiency, higher quality NVs with longer coherence times, also waveguides with lower losses and more tightly confined modes, which will lead to higher count rates, which are very important for both quantum information and quantum sensing. And then, of course, an integrated optolytic chip is completely sealed is the next step in our research. In addition, along with Alexander Kubanek, but also Paulo Oliveira, we're looking at a hybrid technique. So one disadvantage of femtosecond laser writing is it's a microfabrication technique. And so we cannot place NV centers near the surface at nanometer depths below the surface of the diamond. And for a lot of quantum sensing applications, you need these NV centers to be very, very close to the surface, again, nanometer depths. And so what we're thinking of doing is combining ion implantation to form the NV centers, but also even other group 4 emitters such as silicon vacancies, which are compelling for quantum information, and also combining this with laser-written photonics and laser-written microfluidics, and that's ongoing work. But I'd like to acknowledge the two ongoing projects we have, one European project and also an Italian project. And thank you so much for your attention.
Thank you, Shane, for the great talk. Lots of impressive and really exciting results. It seems that Diamond offers so many opportunities for adding functionality. So really a lot of things that can still be done, really exciting. Any questions from the audience? I see there is, at this point, first question in the Q&A box, question from Preska Tivari. What is the coupling efficiency between the NVs and the waveguide, and what is its main limiting factor?
Okay, so our coupling efficiency is quite low. I have to go through the initial papers. This is work done in collaboration with JP Haddon, initially in Calgary, and now in Cardiff. Our coupling efficiency is low. And the problem is our waveguide modes. You know, again, we have a microfabrication technique, and we have waveguide modes that are roughly 10 microns in size, as shown here. And what we'd like to do is reduce that mode size through there are various techniques we can do in terms of engineering the waveguide cross section. To show a very quick picture here showing coupling efficiency as a function of waveguide size. Focus your attention on the yellow curve, and as we go to smaller full width half maximum, so smaller modes, we expect to really rapidly boost this coupling efficiency. As of now, it's really too low to achieve important quantum information devices. But through a combination of, for example, we're thinking of using in the SLM, as shown in the great previous talk by Sven, which will give us more control over those sidewalls I showed before of that make up the waveguide cross section. And the idea is to engineer the waveguide cross section to reduce the mode size. And that's ongoing work. We have this initial result, and we hope to improve upon that.
Thank you. Actually, I also have a question about the success rate for writing NV centers. So you mentioned that it's about 50%,
yes,
if I'm not mistaken. So yep. If you aim at really writing a single NV center at a given position, do you then write 2 of them to make sure that at least one of them is functional? Indeed. Or what is your approach?
Indeed. So the initial sort of proof of principle, I don't have to have a picture here. Let me go back to this, for example, shows the single NV center we formed, a schematic of the single NV center we formed at the center of this waveguide. But this device, to be honest, I mean, it's shown in the paper as well, we actually wrote 5 static exposures within this waveguide, and 2 out of 5 worked, okay? And we've done really more comprehensive studies where we demonstrated this 50%. But the good news is through real-time feedback, by looking at the spectrum, you can actually see you can actually monitor as these single NVs are produced, and then switch and quickly turn off the laser afterwards. This is something we're incorporating in our research right now, but in theory, it adds complexity, of course, to the setup, because right now all we have essentially is a focused laser beam with a very simple vision system to look at, the microscope view of the waveguide, okay, the modification. But adding this extra spectroscopy and this real-time feedback, we can actually get close to 100% success rate. And so that's something we're working towards the future. If we have enough funding, well, it's something we can build into our laser fabrication setup.
Yeah, that's really impressive. Thank you. Any other questions from the audience or from the panelists?
I do have from the panelists.
Yes, go ahead, Tatev.
Thank you. Thanks, Shane, for this amazing talk and very interesting overview on the possibilities on diamond, as Natalia already mentioned. My question is related to the microfluidic parts, because as I understood, this can be a next step for integrating everything on one. So you have the diamond waveguides, you have the microfluidics there. Is there already any application done towards this, or is something new and more research needs to be done? Because I'm already interested in that.
Yeah, absolutely. This is one of the very hot research area. So diamond, in terms of laser writing in diamond and making these microfluidic structures, we're really the first in the world to demonstrate you can make high quality channels. Now, ideally, we'd like to actually form buried. The reason why is they'd be pre-sealed. This chip here has to be sealed afterwards, okay? It has to be sealed with some kind of cover slip. To seal it with another diamond cover slip might be a bit of a challenge. People have shown, for example, the laser welding of two glasses together. So you could think of sealing, if it were made of glass, you could do it. So we're currently exploring methods to seal this in the best possible way. The next step, of course, in addition to the sealing, is producing the ND centers adjacent to the microfluidic channels, but also thinking of incorporating even waveguides to bring light into the setup instead of using free space optics. So you can think of integrating microfluidics, waveguides, and the ND center function, quantum sensing functionality, all in one chip. But this is really very new work, and so we have a long ways to go here.
All right, thank you very much. So good luck on that.
Thank you.
Any other questions from the audience? If not, let's thank Shane again for the excellent talk. Thank you very much. And unfortunately, the third speaker of this session, Jinhui Yin, she had to cancel because she's ill. And so that's really a pity, but we have turned this time slot then in an additional time to take a break. So we will have a break until 3 o'clock. We will start again then with the two last invited talks of today. And so please feel free to use the break as you see fit. Take a coffee, have a cup of tea, or if you want to go to the poster session, for those who didn't have the chance yet, you can still do that. My colleague Tatev, she will put the link in the chat to go to the poster session, and please feel free to have a look and to network in the Gardertown space. So we will see each other again at 3 o'clock for the two last invited talks of today. Hello, Huanzhen. Welcome to the conference. Do you want to try testing the screen sharing for your presentation?
Sounds great. Thank you.
Go ahead.
Try. Share. So it says this will stop other screen sharing. Will that be fine? I think if I share, it will stop.
Yeah, yes, that's
okay.
fine. Yes, go ahead.
Let me see. Screen. Here we go.
Yes, perfect. Looks great.
Looks nice. Okay,
yeah.
okay.
Perfect.
Try.
Thank you.
That's fine, right?
Yes.
You can hear me and the sound is fine as well, right?
Absolutely. Yeah, perfect.
Awesome. Cool. Thank you.
Hello, Rajesh. Welcome to the conference. If you want, feel free to test your screen sharing for the presentation.
Sure. Hi. How are you?
I'm fine. How are you?
Good. Thanks. Hold on 1 second. Are you able to see this?
Yes, we see it in PowerPoint mode. And I guess when you go to presentation mode, it will be fine. Yes, perfect.
Great.
Yes. If you want, you can keep your slides on the Zoom screen. I mean, you're the first speaker anyway in the new session, so you can keep the presentation open so that we can get started right away.
Sure. Happy to do it.
Okay, great. So we'll wait for 5 more minutes until, for 5 more minutes so that participants can come back from the break, and then I will introduce you and you can start the presentation.
Awesome. I'm going to go grab some coffee.
Sure, go ahead.
Thanks. Can you see my cursor?
Yes.
Okay, great.
Welcome back, everybody. I hope you had a nice break, and so that we can focus all of our attention for the two last invited talks of this conference. And the first talk will be given by Rajesh Menon from University of Utah in Oblate Optics, and he will be talking about going beyond refractive lenses with microstructured flat optics. And as usual, if you have questions, feel free to post them in the Q&A box. Rajesh, the floor is yours.
Great. Thank you very much, Natalie, and thank you, Anya, for the kind invitation. I'm very happy to present, and it's a great way to make lemonade out of the lemons of COVID that has been given to us this year. The opportunity to attend virtual conferences from around the world. So thank you for having me. So first of all, I want to talk a little bit about why are we interested in flat optics? Flat optics have the potential to dramatically reduce the weight of imaging systems. So this is a chart put together by Philip Hahn at Northrop Grumman last year or so, where he plotted the weight of optics versus its aperture size. So obviously, as you scale the aperture size, so the diameter, the weight increases, of course, in a nonlinear fashion for conventional lenses, because you need a bulk material in order to refract the light. However, it turns out once you go to flat optics, the increase can be dramatically reduced. This actually becomes even more significant, of course, at very large areas. Now, I'll mention briefly why that's important, particularly related to astronomy and space applications. However, we can zoom into essentially the front part of this chart here to understand clearly some actual numbers, to put actual numbers on this. So here we have 4 charts ranging from commercial lenses. We just picked the flare lenses, which are actually fantastic lenses, very high quality, but clearly also much heavier than the others. Conventional planar convex lenses. And what we refer to as flat optics, as I'll explain shortly, they can be directly etched into dielectric material like silicon, zinc sulfide, diamond, whatnot. Or they can be patterned into some polymer, like polyimide. We were interested primarily in polyimide because of the potential qualification in space. Even at a diameter of something like a tenth of a meter or so, we can potentially get an order of magnitude reduction of about 1000x or so. So it can have a pretty significant impact. So this is the main reason we started looking into this. Now, of course, this is a fairly old idea, centuries old, more than a century. I just picked some work that we did many years ago, where we showed that one can actually design binary phase zone plates, which are, of course, have been around for over 100 years. But they can be actually extended into numerical apertures, which are larger than 1. And of course, in order to do that, you need to go beyond air. So in this example, we simply exploited work done in microscopy to do a water immersion lens, where such a zone plate was fabricated in silicon nitride. So you can actually see the details here. So it's a fused silica substrate with patterned silicon nitride. There's a chromium mask on the outside. So this arrow is actually wrong. It should be just on the outside to form the aperture. Now, the water fills in these gaps, and water and silicon nitride provides the index contrast to provide the appropriate phase shift. So this corresponded to a numerical aperture of 1.14 and an F number of 0.42. And we can actually characterize this very carefully to show that indeed it does work as predicted by theory. So these are the dashed line here is the simulated point spread function, and this is the radial cut. So you're only seeing a rotationally symmetric point spread function as a function of the radial distance in microns. The dashed red line is a simulated point spread function in air, and as soon as you add the water, you get the squeezing effect as expected. And the crosses are the experimentally measured values. The experiments themselves are quite tedious. If you're interested, you can read the paper. But clearly, they work quite nicely with the predicted performance. But of course, we are all taught in undergraduate physics that diffractive optics has chromatic aberration. So this was a fairly fundamental problem for imaging. So we started looking into this for the purposes of non-imaging optics, not for imaging, which I will come back to towards the end of my talk, really related to solar concentrators, which I won't have time to talk about, but if you're interested, I'm happy to discuss in the Q&A. Of course, for solar concentrators, one needs a very broad response. So that's where we came to. So we started looking into, really what are the fundamental limitations? And we're still in the process, so we don't have very clear answers, I must admit. But a lens is an element that simply takes the incoming plane wave and converts it into some sort of converging wave. And I've represented these as spherical waves coming to a focus. And there's quite a bit of theoretical work which has shown that the optimum focus really depends on your goal. But if maximal power concentration is your goal, this focus really, the fields of this focus really has to conjugate with the field of electric dipole, because which is somewhat expected, right? An atom is the smallest emitter that we are aware of today. However, for imaging, of course, we are not necessarily interested in the theoretically optimal concentration of light. In fact, for imaging, we're interested in something much simpler. If we focus on the complex field in the focal plane, of course, it's a complex number. I'm talking about scalar fields for the moment because we can treat each component of the electromagnetic field as independent in the case of the homogeneous medium. So we have the amplitude and the phase. And what we're really interested in is to really localize the amplitude. And again, I'm plotting this in a radial coordinate system, assuming radial symmetry for the sake of simplicity. However, the phase itself is actually unconstrained, or so it seems. And the reason is quite simple, right? Because when you do imaging, you actually take the field and take the absolute value square of it to get the intensity, and that's what the vast majority of sensors will record. In other words, when you take the absolute value square of this field, the phase is essentially gone, right? You square it, it's gone. So this, in paper, you can tell, okay, this is not terribly important as long as the amplitude is localized. Another way to think about it, if we want the form of the field where you have amplitude that's fairly localized, the phase that could potentially be a free floating function, unconstrained, and one can assume time harmonic fields for the vast majority of purposes. Again, we're talking about linear optics. Of course, nonlinear optics presents its own interesting opportunities, which I want to talk about. Now, I meant when I say the phase is unconstrained, this is actually strictly not true. Of course, the entire field must satisfy the Helmholtz wave equation, so that imparts some constraints on the function that can perform as phase. However, conceptually, this tells us that if I put a localized field with an unconstrained phase, with some constraints, let's say, but minimal, weakly constrained phase, weakly constrained by the Helmholtz wave equation, and apply back propagation, then I am not necessarily limited to these nice converging spherical waves or even the conjugate of the electric dipole, as theory shows. It turns out there are many other waves that can actually induce the focusing. So another way to think about what I'm trying to say here is that phase in the focal plane is a free design parameter that allows us to essentially pick the phase in the black box here that can turn the plane waves into some formulation, some superposition of waves, which will end up with a focused amplitude or focused intensity. And this theory is not fully worked out. I think there's lots of people trying to understand what the limitations are. And really, what goes in this black box is what has become very exciting in the most recent years. There are flat lenses that I will discuss today. There are meta lenses, there are meta surfaces, there are all kinds of course, refractive lenses and combinations of the above. And I'm going to focus on flat optics primarily, but clearly you can put anything here to some extent that performs this linear transformation. Now, if you apply this in a numerical sense, you can come up with very broadband diffractive lenses where the chromatic aberrations have been corrected. And I'm just showing you several examples where we allow the phase in the focal plane to be a free parameter and come up with, in this case, rotationally symmetric diffractive lenses. It doesn't have to be. Where the feature sizes are free varying. These are the heights as a function of radius. And if you look at the pupil phase function, which is basically what goes in this black box, that looks like what's shown in this blue curve for a particular wavelength. In this case, I picked 450 nanometers. And you can compare that to the parabolic phase function, which we are all taught in undergraduate or high school physics on what the lens should look like. And that's what that is. And you can clearly see they're quite different. And even more interestingly, this phase, of course, varies with the wavelength. So we can look at them at different wavelengths. I should point out that these lenses are fabricated using grayscale lithography using various tools, but primarily we work with the excuse me, laser pattern generation. And I should acknowledge quite a bit of support from Heidelberg Instruments for the same as well. I should also acknowledge significant prior work, primarily from the context of signal processing by Wirowski and others in Europe, and Joe Mate and others in the US in the late 80s and early 90s as well. So this is really inspired by some of this previous work. As I mentioned before, this particular lens is actually broadband, and it's broadband over a pretty big bandwidth, going from 450 nanometers to 1,000 nanometers. The pupil function is no longer achromatic. So here, what we're showing in the insets, just for a second, the top inset is the geometry, so the radial distribution of the rings, the heights of the rings, and the different colors here represent the phases at different wavelengths, going from 450 nanometers all the way to 850 nanometers in the near infrared. Clearly, every phase distribution at each wavelength is different, and each of them are different from their corresponding parabolic phase distributions as well. But if you take each of these phase distributions and allow this phase to propagate into the focal plane, which in this example was, I forget the exact number, but a few millimeters away, you end up with tightly focused points per functions. So this is again showing the simulated points per function at different wavelengths, which is the square of the complex field, so the intensity. So the phase in the focal plane is now discarded as expected in a sensor. Of course, we are interested in experiments, so I'm just showing you a couple of examples of flat optics that we have worked on in the past. So first of all, this is what our device looks like. We typically make them on a glass wafer. They're patterned with a polymer on top, typically photoresist, sometimes other materials. And we simply place the flat optic with a small spacer in front of a CMOS sensor. And we take images like this. So this is an example of a video under sunlight. It was just raw image from about 5 years ago, where we can show pretty good achromatic performance. Just key metrics here, the weight's quite low, some fractions of grams. The thickness of the active substrate is probably the thickest element here, and it's about 0.5 millimeter. Of course, we can go a lot thinner. We're going down to about 25 microns or so. The aberrations can be quite low. The actual device thickness itself, which you can get from here, is only a few microns. But of course, the support substrate is much larger. And the strain ratio can be quite high as well. Of course, there are trade-offs involved, which we're still trying to really understand what the real trade-offs are. So, so I won't talk too much about it, but there's clearly some trade-offs related to efficiencies and so on because of the discretization of the phase that goes on here compared to refractors. And we call our flat lenses multi-level diffractive lenses, or MDLs, That's my terminology. So I'll show you a few more examples. You know, it is possible to get very large numerical apertures using these approaches. This is an AF 0.9 designed for 850 nanometers, with a diameter of 4.13 millimeters. And it had some interesting hierarchical structures with very relatively small teeth sitting on top of relatively large structures, as you can see also here. And these were fabricated in the advanced research labs at Heidelberg, actually in Germany. And you can see they're pretty challenging to make from a grayscale perspective. But in principle, once you make it, you can make this, use this as a master mold and use it for replication using imprint lithography. But because we do not require very high refractive index for the final device. And this is simply just showing a measured points per function of that previous lens, which shows very tight focusing and so on. The MTF is shown here for comparison. You can get several thousand in terms of line pairs per millimeter as expected. So it follows the theoretical prediction quite well. Of course, these ideas are not limited to visible or near infrared. We're agnostic to the band as long as there are materials that are transparent. So this is an example in the long wave infrared, which we demonstrated a couple of years ago, where we had relatively high numerical aperture, 0.45, relatively large diameter, a little more than half an inch, and a pretty big bandwidth going from 8 to 14 microns. In this case, the lenses were made on silicon, because silicon is transparent, and there's a relatively thin polymer, something like 10, 12 microns thick on top, which was patterned. And I'll show you shortly that that's not a limitation. You can go straight into silicon as well. So you can see what they look like, and they're coupled with, in this case, Seek thermal infrared camera, and we also used it with a FLIR infrared camera. You can see images which are reasonably good. Not fantastic. More recently, we actually extended this approach to monolithic all silicon devices. So where in this previous case, of course, we have to do grayscale lithography on the photoresist or some polymer or somehow have some approach to do the replication, which I will also talk about briefly. But here, what we do is we do a multiple lithography and etch process. So we define a lithography, do an etch, and define another lithography and etch, and so on. So following multiple aligned steps like that, you can get multi-level structures again, and directly into silicon. So these are examples, and you can see a picture of it. And there's the FLIR Tau2 camera, and those are pictures we took. And what's really interesting is with some relatively simple post-processing, in this case, just very standard conventional filtering, you get images that are pretty comparable to what one could obtain from a zinc selenide refractive lens. By the way, this is a corrected refractor, so it's not a single surface or a two-surface lens, but it's got several elements in it. I think it's either a doublet or a triplet. But it's about 65 times heavier in comparison. What's even more striking is that this approach can be extended to pretty dramatic bandwidths as well. So this was something we demonstrated, again, a bit more than a year ago, where we showed that a single lens could actually be achromatic over a world record bandwidth from visible to long wave infrared. This is quite remarkable, because it wasn't even clear that this should be possible. And it's clearly not possible with conventional optics. And the approach is very similar, but the experiments are a bit more complicated. So primarily because there are very few materials that are transparent over these huge bandwidths, and also there are no sensors which we can use to measure all these wavelengths. So we actually had to do a bunch of, quite a bit of hacking to actually get this working. And if anyone's interested in the paper, I'll just focus on the results, where you can imagine taking a picture of an object. Perhaps the soldering iron is a better option. Take a picture of an object in the visible, but it's not quite clear if the soldering iron is hot or not. However, because the same lens can provide a thermal image, you can actually tell, okay, it is actually hot. So that's an interesting application where you can get a lot more information about the same object by looking at it in different bands. So it's a form of extreme spectral imaging. So this is a visible image, this is a near infrared image. Again, interestingly, in the near infrared image, for example, some of the details of this toy car disappear as expected, but you can see other details. Excuse me. And this is in the infrared. Now, these things are taken in different bands because we are actually using different filters in front of, in these two cases, silicon detectors, and in these two cases, various forms of microbolometer detectors. This bottom row is done with a FLIR camera. This is done with something called a electrophysics camera, which has a bigger spectral band. And you can get fairly nice performance, good resolution, and so on and so forth. Oh, I should also mention, in order to actually get this to work, we need to use substrates like diamond or something that is transparent. We also did another way to do the experiments where we actually make the lenses on two different substrates, the exact same lens on a silicon substrate and on a glass substrate. So use the glass to measure these and silicon to measure these as well. But essentially it's the same lens, just different support substrates. The ideas can also be extended to very, very large lenses. So this is an example of a more recent work where we extended this to what I believe is the world's largest flat lens with a diameter of 100 millimeters. So this is a 6-inch wafer. And by the way, the only reason we could make this was because we recently, about a year ago, purchased a DWL from Heidelberg, which allows us to make these large areas. Of course, one can also imagine using segments and aligning them, which is what's done in the case of space telescopes, which are, of course, much larger in terms of aperture. So that's really something we are working towards. But it's a good demonstration of what we think is possible in a single ride. This focal length is 20 centimeters, so it's an f2 lens, again, fully achromatic from visible, and a little bit into the near infrared, 400 to 800 nanometers. And this is a very simple experiment. We took a white flashlight, expanded it, and focused it down to a spot size of something like 2 microns. And if you really think about this, this is an incredible concentration factor for something like 250 billion or so. So it's sorry, about a 2,500 billion or so, sorry, 250 billion X. So it's a pretty insane amount of concentration. In fact, of course, if you put this under sunlight or something like that, it's quite a dangerous experiment to some extent to do. And it works. It's quite achromatic. We were able to measure the focal spots as a function of wavelength, going all the way from 400 to 800 nanometers over almost a continuous spectrum. Here I'm showing 50 nanometer steps. We actually did this at even smaller steps, very small deviations. Of course, it's not perfect as one would expect from a refractor lens. So there's still work to be done in improving the Strel ratio here. So we're not quite there yet, but it's quite promising. And more interestingly, we can actually use it to take images of astronomical objects. So for example, we built a home-built setup where we simply place this large camera in front of a standard image sensor in a little box, and we pointed at the moon in the last fall, one clear night. And we can take images. It's not perfect again, but clearly it works, and it's fairly achromatic. You don't see any chromatic aberrations and things like that. The main issue really has to do with the fabrication errors, where we're seeing quite a bit of scattering of light, which of course we could deal somewhat in post-processing, but clearly would like to deal with in solving the fabrication errors, which is what we're actually focused on nowadays. Another aspect of this approach of using phase is free parameters, that you can do other crazy things like increase the depth of focus of a camera. So this is an example of a lens where we increase the depth of focus by almost 4 orders of magnitude over what's expected in a conventional lens. So let me explain what that actually means. So this was the particular lens we used, but we're not limited to such relatively small lenses. And this was 850 nanometer lens. The idea was that we wanted to focus the light to a very tight spot, about, in this case, 5 millimeters away from the lens. It's about 12 micron spot. So a relatively large F number. But we wanted to maintain that focus as you move away from the lens. So we want the light to be very tightly focused all the way up to a little more than a meter. So this is, again, going from 5 millimeters away from the lens to about 1.2 meters away from the lens. So that's a pretty incredible number, about 4 orders of magnitude larger than what one would expect from a diffraction emitted lens with the center focal length about there. So this is kind of nice because now you have a very tightly focused beam, which you can use for LiDAR or whatnot. But in our particular case, what we did was we wanted to see if we can do imaging with it, because we wanted to see if we can actually use this to take an image like a conventional camera with some field of view. And indeed, that's what we did. So the details are in the paper, but let me just focus on this image here first. So there's our sensor. The lens is behind the sensor, so you can't, in front of the sensor, so you can't see it. And we had a bunch of objects illuminated by the near-infrared flashlight. So this is a near-infrared LED illuminating that toy. It's another light illuminating this little resolution chart and little toy and so on and so forth. And if you take the picture, this is what you see. You see the toy in focus, which is about 200 millimeters away from the lens. There's a resolution chart a little more than a meter away, and there's a toy car 2 meters away. There's a thumbs up sign about 4 meters away, and way back there, almost 6 meters away, you can still see the resolution chart. And in comparison, if you take a picture with the Google Pixel 3 camera, you can see, okay, if you focus on the toy, everything else is very heavily out of focus. Now, of course, it's not an exact comparison because the F number of the Google Pixel 3 is much lower than the F number of this camera, but it gives you a sense of what we think is possible. So that's an interesting application. Towards the end, I just want to talk about additional flexibility in how we do these designs. We can think about free-form broadband flat lenses. So as an example where, instead of having rotational symmetry, we can actually have break the symmetry into simple square pixels, and again, apply the design algorithms and come up with lenses which do pretty strange things. So in this example, we made a lens that forms a square focus spot. Of course, this is a schematic. The light actually does not have these sharp corners here, so my student went a little crazy drawing up the schematic, but the idea is that if the lens can form a spot that is a square, as shown here, tightly focused in this case, and this is a different lens which can form a square which is slightly bigger. So the key point is that the size of the lens is the same, but the size of the spot changes. So say F number is the same, the diameter and the focal length, but the points per function of the focal spot is engineered. And that is the sort of flexibility that is very difficult to do if you're working with a refractive lens or a single refractive lens, of course, but one could potentially do with multiple refractive lenses. But this is possible with a single surface on a broadband, free-form MDL. And these are images taken with different lenses. So this is the L3 lens, we don't have a picture of it, sorry. And you can see the good color rendering, fairly good broadband performance, and so on. I mentioned that we can potentially fabricate this with nano-imprint lithography. I'm just going to show you one example where we made a master pattern and then we were able to imprint into this with a conventional CMOS nano-imprint process. I should say conventional nowadays, not necessarily truly conventional. But this is a centimeter diameter lens where we can form pretty good imaging in the visible. I'm going to skip these slides. I'll also skip that. And just to summarize, as I said before, we're somewhat agnostic to the NM spectrum. We can demonstrate this all the way from the visible all the way into even the terahertz and so on. We haven't done a single lens for all the wavelengths, but I think that's not inconceivable at the current state of affairs. The last topic I just want to mention is that these, as I mentioned at the very beginning, these techniques can also be applied for non-imaging optics, solar concentrators, as I mentioned in the very beginning. But of course, you can apply these to holograms as well, which are somewhat simpler to understand and do and so on. This is an example of a spatial spectrum multiplex hologram where in the visible band, it produces an image of a very colorful heart, as you can see here. There's some ghost images you can see, but primarily that's the image. But if you illuminate with the near infrared light, it forms the silhouette of a lion, which of course, this is invisible to most humans, right? This we have to capture with the cell phone camera or something like that. So this is kind of like a secret key that is hidden within the hologram. And this is just a nice video that we took under sunlight. So when you place a visible cut filter, you can see the silhouette of the sun, and when you remove it, the heart comes back. So it's a truly spectral multiplexed hologram onto a single device, again, fabricated using grayscale lithography with the similar techniques that I just talked about. You can extend this to 3D holograms as well. This is my last slide, basically, where we showed that you can project an image that changes as you move away from the hologram. So as you move the screen further and further from the hologram, the arms of this clock essentially rotate, as shown on the top here. So, which is interesting because here now you're trying to control the propagation of light based on phase distribution on a single plane. If anyone's interested, these works have all been published. So thank you for your time, and hopefully I've given you some examples of what we think is possible by some combination of understanding of the theory, computational techniques, and advanced lithographic approaches in the 2.5D, 3D regime. I'm happy to take questions, and I should acknowledge support from various agencies, as well as a fairly broad team of folks who worked over the years on various aspects of this project. Thank you.
Thank you for the really great talk. Very impressive results. Several record values have been shown in your presentation. Really, I was not aware of the fact that those top-level achievements could be done with a single lens. I'm really impressed. So, are there any questions from the audience? Perhaps I
can't see anything in the chat, but go ahead, sorry.
I don't know if there are questions. I don't see any at this point, but I have perhaps a small question to start with. So if I understand, if I understood your presentation correctly, you mostly use plane wave illumination for your experiments. Have you tried Gaussian beams? I'm talking about laser beams. Does it make a big difference in terms of performance?
Yeah, that's a good question. I should say, when we actually do the design, we assume plane waves just for simplicity. And if you really think about most of the experiments, of course, we have to have either truncated plane waves or Gaussian beams just from the constraints of the experiments themselves. So the difference is quite minimal. And of course, when you do conventional imaging, like with ambient light, this is unpolarized. And of course, spatially, I would say, partially coherent, right? Sunlight has a coherence length of something like 100 microns or so. So it's, of course, there are some limitations. So for example, if you go to completely incoherent light, there is a theorem from Van Zernicki theorem, which tells you that diffractive fringes should disappear as you get to incoherence, which clearly happens. So there are limitations on what is possible. So I don't want to say it's completely general, but as long as you have a certain level of either spatial coherence or spectral coherence, which is the example that you're talking about, then treating these lenses with plane waves and testing them with non-plane waves is a fairly small perturbation. Mm-hmm. And you can show this theoretically as well. But your question perhaps is more related to whether these things can be used for beam shaping or coupling, mode matching and things like that. The answer to that is yes. I think so. We haven't really pushed those applications, but it's definitely possible, I believe. For mode matching, the thing to also think about is that you might want sub-wavelength features, and then you end up in the regime of not necessarily diffractive optics, but clearly in that gray area between meta surfaces and diffractive optics. Mm-hmm. And lots of folks are also looking into those into those devices as well.
Thank you. Perhaps a small follow-up question. You referred indeed to practical applications. Is there one killer application that you think of right now where you think that, okay, this could be implemented in a commercial product with these features within the, I don't know, coming 5 years or so?
Oh yeah, definitely. So if you really think about what the main advantages really was in my first slide, I think there are many advantages and there are many potential applications, and we're looking at various things, but in my personal opinion, the reduction in weight is a pretty dramatic advantage. So that's where I believe that there is a pretty big application related to anything that's airborne. So you can imagine, cameras for firefighters, where the range of the UAVs are limited essentially by the weight of the optics. Something like, I've heard numbers where something like 60 to 70% of the weight of a camera is essentially the optics. So if we can cut that down to, I don't know, 20, 30%, that can increase the range of a UAV by a factor of 5 or something like that. That's a pretty dramatic improvement.
Yeah, absolutely. Yeah.
And of course, anything related to space. So this is something we are very interested in. Is if you look at optics on small satellites, which are proliferating, launch costs are pretty. Of course, they're coming down, but they are directly related non-linearly to the weight of the payload. So if we can, whatever we can do to reduce the weight of the payload is quite valuable.
We still have one question also in the chat box. Question from Preksha Tiwari. What kind of imaging viewing angle range can you cover with a 3D hologram?
Yeah, that's a great question. Actually, in the example that I showed, the viewing angle is relatively small. We didn't actually measure it, but if I were to eyeball it, it would be in the order of 30 degrees, something like that, full angle. But perhaps your question is, I guess I should preface it by showing the video that I showed. So for example, this video is taken at a very steep angle, right? So it's an incoherent image. First of all, I forgot to mention this is white light, right? So that by itself is interesting because this is a white light hologram, not necessarily a laser light. This is using a flashlight, by the way, the flashlight of your phone, for instance. And we're taking a picture at a very steep angle here, of course. So because it's incoherent, the observer's viewing angle is actually quite large. Yeah, so that would be my first comment. But perhaps your question is more related to the viewing angle of a lens, because that's maybe more relevant. And that's a fairly challenging problem, and we haven't actually solved it. I don't think anyone has actually completely solved it. There's been a couple of papers which have shown that you can use meta lenses to get very large viewing angle. However, the trade-offs are quite extreme. You have to give up efficiency quite dramatically in order to achieve this. And there might be some fundamental reasons why that is the case. We're not quite sure yet. Sorry, it's a long-winded answer, but I don't know.
Lots of information, but as I said, very exciting results. So, there is another question in the Q&A box from Simone Sorgato. Can you comment on the current? Did you have to take special measures given the huge bandwidth?
Oh yeah, that's a great. I don't know what quarant means, Simone, but
it's coding.
Oh, coding.
Oh, okay.
Great question. Yeah, so you're absolutely right. Today, as far as I know, I'm not a coding expert, but as far as I know, there is no anti-reflection coding that can operate over this such a big bandwidth. Of course, increasing the number of layers is one way to go, but as far as I know, no one's actually done this. Of course, in the solar cell community, there's quite a bit of work with incoherent light, or let's call it partially coherent light, with various coatings and so on, particularly related to the use of silicon nitride on top of silicon. Now, we haven't done any of that for this experiment. Was very naive. We simply made the lens either on a diamond substrate, CVD diamond, or a silicon or glass, no coatings at all. So we haven't even done anything like that as what you're suggesting, but these are things we're looking into. In fact, this is a very practical problem, is that, you know, when the lens is no longer the limitation of the bandwidth limitation now is coming from the sensor, because there's no sensor which can accept those photons, plus the coatings and all that, the other aspects. So it's a very interesting regime to be in. Anya, you have a question?
Yes, I have. Maybe it's a kind of crazy suggestion, but I'm very curious. So you're showing these flat lenses, right? So these are grayscale structures that are essentially made on flat substrates. Do you think it would be interesting to look into somewhat curved substrates and pattern them with grayscale structures on top? Like, would that be of any practical value?
Yeah, I think that's a fantastic suggestion, actually. I think there are folks smarter than me looking into this. We are not quite doing this just because of the challenges that I see in the manufacturing, but I think folks are interested in this primarily because you can then now trade off two things. You can trade off the power, right? So here, when we design these lenses, the microstructure is providing the power for the lens. But if you can split the power between the diffractive structure and a refractive surface, as you're suggesting, then there is probably some advantage in the sense that your requirements on the diffractive, on each of them, can go down. The second reason why people would try to do this, and this is an old reason, in fact, Canon did this in the 80s, I believe, is to correct for chromatic aberrations, because the refractive chromatic aberration is the opposite in sign with the diffractive chromatic aberration. So these things are, I think, quite important, what you're suggesting. We just haven't looked into it carefully.
Right. Okay, because I think you could still go, I mean, you would probably still have some room within the dynamic range of your autofocus, right? But I don't know if that would already give you the regime in which you can compensate these two aspects.
Yes, you're absolutely correct there as well. In fact, it turns out we are working on a project where we are interested in curved detectors. So as you are probably aware of, focal planes are not surface planes, right? In theory, they're always curved. So people are trying to curve the detectors to, you know, minimize aberrations. So then the question becomes, okay, can you design flat lenses to project PSFs onto curved surfaces, which is weird to think about. But one way to think about it is exactly what you're suggesting. Could you curve the lenses in order to match the curvature of the sensors? I think these are all open questions. You know, I think people are looking into it. My concern has always been on manufacturing, which I believe some of you on this panel are probably more qualified to answer than me. So.
Okay, thanks.
Okay, very good. So if there are no other questions, thanks again for the excellent talk.
Thank you very much. Appreciate the invitation.
And thank you. And then we can move on to the very last talk of this conference. It's great to see still such a big audience. And so the speaker that I will now introduce is Huanzhen Zhao from Stanford University, and he will talk about scalable nanofabrication towards biomedical applications using chemical liftoff lithography. Please, the floor is yours. I think you have to unmute your microphone.
Here we go.
Yes.
Okay. All right. Thank you very much, Leslie. And good morning, everyone from California, as we are still quite young of the day, now around 6:40 a.m. And good afternoon and good evening to folks joining us from elsewhere in the world. My name is Huanzhen Zhao, and I'm currently a postdoc scholar in Professor Jen Bao's lab at Stanford. And I'm very honored to be invited to speak here today. Thank you very much for organizing this fantastic event. And thank you, Dr. Michelle, for inviting me here. Today, I'm going to share some of my PhD research that I did at UCLA with Professor Paul Weiss and Professor Ann Andrews, mainly on using soft lithography on nanofabrication towards biomedical applications. I hope to provide you some insights of how the soft lithography can open up some opportunity for biomedicine, and to show you guys some interesting stuff at the end of this whole talk events. Recently, the development of bioelectronics has enabled a tremendous opportunity to monitor the health condition. And the seamless merge between human body and the machines has enabled exciting opportunities to understand our body, to monitor our health conditions, and to even provide better treatments. There are mainly two categories of bioelectronics, including the minimal invasive or the implantable device inside the body, and also the wearable device on the skin. And those signals can be transferred via the quickly developing Internet of Things to the cloud and also the hospital, and can provide closed loop feedback remotely. As the development of the broad application, the need increases for devices with high integration and multiplex functionalities, where the nanofabrication techniques are highly demanded and are at the heart of the next generation devices. Here we give you some examples on the application enabled by novel nanofabrication approaches. For example, the nanofabrication strategy has been applied for wearable electronics device for electrophysiology recording, and also on the implantable neural probes for in vivo recording, and other also basic electrical units such as the photovoltaics for wearable LED. Therefore, the nanofabrication approaches have enabled very broad biomedical applications and will provide more and more exciting opportunities. Now let's take a step back and take an overview of the general nanofabrication approaches we have. Generally, there are bottom-up and top-down approaches for nanofabrication. The bottom-up approaches generally assemble nanostructure from molecular level, like growing nanomaterials from their precursors. And the top-down approach, on the other hand, fabricate nanostructure using the size reduction from a bulk material, like the commonly used lithography approach. Bottom-up technique can produce nanomaterials with high quality. However, those strategies have poor control over the orientation of the S-grown nanostructures. As shown in those figures on the top right, the nanowire distribute randomly between those electrodes, and therefore it's very hard to control over the reproducibility of the fabricated device. Top-down approaches, on the other hand, including those photolithography and electron beam lithography, are widely used in semiconductor industry to fabricate nanomaterials. Top-down materials enable precious control over the final shapes, size, positions, and also the orientations of those devices. And it can provide the ready integration with the device with high producibility. As shown in those figures on the bottom right, those nanowire size, number, orientation can all be controlled preciously, leading to a highly reproducible device. However, there are challenges in the current top-down fabrication process. As everyone here already knows, fabrication in nanoscale can be time-consuming, low cost, and also expensive. In most cases, nanofabrication requires fancy tools such as electron beam lithography or extreme UV machines. For example, the step for the EUV made by ASML is over $120 million per tool. This is affordable for big semiconductor manufacturers like Intel, but it is prohibitively high for small companies and also the universities, which are the main driving force to push the translation of bioelectronics forward. Alternatively, soft lithography emerged as a promising tool for the micro and nanofabrication. Soft lithography uses polymer steps, generally made by polydimethylsiloxane, PDMS, to transfer and print micro and nanoscale features. This technique provides an alternative approach for nanolithography with advantages of high throughput and also low cost. An example in soft lithography is micro-contact printing. A typical micro-contact printing process includes two steps, the fabrication of the steps and the printing. For printing, the PDMS stamp will be immersed with an ink solution. For example, it can be alkyl molecule, and then it can be flipped over and get into contact with the surface. And then covalent bond will form at the contact area to have the chemical pattern of interest. However, there are several problems in this process. One issue is the lateral diffusion of the ink molecule. This issue becomes more significant when patterning in sub-micron scale, as it produces larger feature than expected. To overcome this issue, our groups at UCLA developed a subtractive stamping process named as chemical lift lithography, in short CLL, which has emerged as a promising tool for the micron nanofabrication. In CLL, a self-assembled monolayer of hydroxyl-terminated alkyl will form on the gold surface. Then the oxygen plasma-activated PDMS stamp with silox group will be brought into conformal contact with the alkyl molecule. And the condensation reaction will then occur between those two hydroxyl groups. Upon lift-off of the stamp, it will selectively remove the hydroxyl-terminated alkyl only in the contact area. So this process can produce high pattern fidelity and we didn't absorb any lateral diffusion. And it has been shown to go to resolution down to 5 nanometer, which is around 10 gold molecule across. And a layer of gold molecule will also be removed from the surface as confirmed by the XPS data shown here. Now, with this approach, we were able to pattern micron and nanoscale feature in large scale with high throughput. Our groups have been working on advanced CLL technique for higher resolution and also exploring its application in a variety of fields, which I will talk about some of them today. The first thing we explored is to take the advantage nature of the soft nature in soft lithography. The reason it is called soft lithography at the first place is because we use the softer stamps, the PDMS stamps, for the patterning. Well, soft means they are deformable, that they will change their shape upon applied force. We first demonstrated a polymer pen chemical lift lithography, where the PDMS probes were made by those V-shaped stamps, and we designed the polymer pen with different features, as we can use those big ones, as we show here, as a supported arm, and the smaller ones to produce small features. And we also demonstrated that if you press a probe with different forces, and different features can be achieved. If you press them harder, more surface area are going to be in contact, and that will produce a larger feature in the surface. By designing the polymer pen probes and applying different forces, we were able to produce features down to 30 nanometer. Another quite interesting techniques we developed is based on a well-known phenomenon called roof collapse. Basically, when a small aspect ratio of height and length is applied, the stamp will collapse in the central area, which is referred as roof collapse. Generally, the roof collapse is considered as undesired phenomena that people try to avoid in the soft lithography, as it cannot replicate the patterns with desired features. However, I always believe that there's no undesired phenomena in science, as each phenomenon can be used as a useful aspect for different applications. One day I was in the lab and thinking, can we learn something from this phenomenon, or is the roof collapse really bad? Well, it turns out it's not for me. Here we developed a new lithography technique called self-collapse lithography, which utilizes those nanoscale channels formed naturally at the edges of microscale feature on softer stamps. By tuning the height, the width, and also the Young's modulus of the stamp, we were able to fabricate nanoscale features down to 30 nanometer. The most exciting aspect in this lithography is a small feature produced from large structures, since the patterning can be achieved using those microscale stamps made by conventional photolithography, which avoid the use of the expensive tools such as e-beam lithography. Using similar approaches, we were able to pattern molecules on different metals and semiconductors using CLL. On the left, those are scanning electron microscope images of the patterned molecule on different metals and the semiconductors with false color, including the copper, silver, platinum, titanium, and germanium, as we expanded them from gold surface. One application of those patterned molecules is for the biomolecular imaging. Here in the red, after the CLL, we can backfill with single-stranded DNA into those lifted off area. Then we can have hybridization with another fluorophore labeled DNA for biomolecular patterning. And in this case, the last one is the SEM images of the patterned molecule, and this is a fluorescence image of the backfilled DNA molecule. And also we have shown that we can use this pattern structure to study the electrical property of the DNA molecule from the surface, the charge through the whole DNA molecule. And this is a separate work. If you're interested, you can check out our 2019 JAX paper as well. So beyond the molecular patterning, CIL can also be used to fabricate the nanostructures. After the CIL, those remaining molecules on the surface can be used for resist as a following wet etching process, which surprisingly works out quite well for the nanofabrication. For example, here the CIL can be used to fabricate those nanoribbon arrays in large area. This one is the SEM image of the patterned molecule on the surface, and those are just molecule patterned on the gold surface, argentile molecule. And on the right, those are atomic force microscope AFM images and also the SEM images of the gold nanoribbons. So we were able to pattern the gold nanoribbon arrays with 200 nanometer wide and 400 nanometer pitch. We can use those gold nanoribbon as plasmonic sensors, as I will share them with you in the following slides. But before that, let me show you one more thing on how we fabricated those PDMS stamps. As I mentioned to you at the beginning, our goal is to have a low cost yet high throughput nanofabrication technique. Therefore, I try to avoid expensive nanolithography tools. To make the PDMS stamps, we will need a mold, which generally made out of silicon, using a relatively expensive conventional nanolithography, such as EBL. Here, we developed a process using the HD DVD, basically at everyone's home for the PDMS, and that can be used for the patterning process. Those DVDs are accessible to everyone, and they are also just a couple of dollars each. So generally, the HD DVD has a quasi 1D feature, which has with the width of 200 nanometer and spaced out at the pitch of 400 nanometer. And it's if you take a look at the DVD, and it has 4 layers, and you can separate them between layer 2 and 3 using just a razor blade, and layer 3 just a dye layer, and you can rinse them off by ethanol, and which give you the substrate of the DVD that can be replicated easily using the PDMS stamps. And those are some atomic force microscope images of the substrate of the DVD and also the patterned PDMS stamp once we replicate the feature from the DVD. Now with this in mind, we can go back to the fabrication. And we can use those HD as mold and make the PDMS stamps and use the PDMS stamp to pattern for the chemical lithography. And we can also pattern the gold nanostructure over centimeter scale on glass. The plasmonic peaks of the gold nanoribbons will shift at the environment of different reflecting index. And we have shown that those gold nanoribbons have a sensitivity around 500 nanometer per reflecting index unit. Moreover, we use this for sensing of a biomolecule, including proteins and lipid vesicles. Here we coated the surface with a nanometer thin indium oxide to study the absorption and desorption of those molecules and on the metal oxide surface. For example, we were able to track the plasmonic peak upon the absorption and desorption of the lipid vesicle and also the BSA on the oxide surface in real time. Other plasmonic sensors can also be fabricated by functionalize the oxide surface with different receptors, such as antibodies. Apart from 1D gold nanostructures, plasmonic 2D nanostructure was shown to have enhanced plasmonic property, and it has better control of their optical properties. We then developed a generic approach to fabricate 2D gold nanoplasmonic device, also using the chemical lithography. Here we demonstrate a double patterning approach, which is quite straightforward that can produce 2D features using those nanoribbon PDMS stamps, which are also made from the HD DVDs. The patterning process is shown on the left. After the first leaf-off process, we clean the stamps and reactivate them. And after rotation of 90 degrees, we put them back in previous pattern 1D surface for another lift-off process, which will generate the 2D gold nanoplasmonic structure arrays. Some AFM images and optical microscope images are shown on the right. As you can see, we were able to pattern those highly uniform 2D gold nanostructures arrays in different features in large area. Those 2D gold nanoplasmonic structures can be used for plasmonic sensing, as I demonstrated previously for those 1D nanoribbons. Going beyond the plasmonic sensing, we are interested in building active electronic components, such as transistors, which has been used widely in every electronics we have, such as our phone, computers, and monitors. We have shown here that we can use the CIL to pattern the gold and titanium source string electrode, which are the key components of a transistor. In an example of the patterned source string electrode with different width and length, you can't really see the difference, but they are on the nanoscale. So this technique provides an alternative approach for the transistor fabrication without the need to go to clean rooms and perform conventional photolithography processes. Field effect transistors have key advantages over optical or electrical chemical platforms for biosensing, including low detection limit, real-time, and labor-free measurements. Our groups have developed aptamer-based field effect transistor biosensors for small molecule monitoring. So aptamers, as I'm showing here, are short DNA or RNA molecule that are pre-selected to bind to a specific target. And those DNA molecules have negative charge backbones. Upon the target binding, as I'm showing here as a purple, that those aptamer will capture the target and have conformational changes, which leads to the redistribution of charges on the aptamer. This change of charge redistribution can be detected by the semiconductor transistor, which is indium oxide in this case. To make biosensors with higher sensitivity, one strategy is to increase the surface volume ratio of the semiconductor, basically make them as nanomaterials. For example, nanowire transistors have been shown to have high sensitivity. We then started to think, can we borrow the knowledge we learned from the gold nanostructure and microstructure patterning and transfer them for semiconductor patterning? We then came up with a strategy to fabricate those semiconductor nanostructures. So to fabricate the nanoscale semiconductor arrays, we came up with different fabrication process that combine with sputtering. And we use the CIL to pattern the gold nanoribbon first, which is the same process I described to you previously. And we can, using the sputtering of the indium oxide on the top, and then we can remove the gold as a template or as a metal mask, and to have those patterned indium oxide nanoribbons. And this process is not restricted to, or not limited to the indium oxide, but it can also be used to other materials fabrication as well. Here are our results of the patterned indium oxide nanoribbons. Those two are atomic force microscope of the topography of those nanoribbons before and after the metal removal. This was super excited when I saw those, when I compare those patterns, as they overlap quite well with each other. As you can see, the height profile here, and indicating there we have a very perfect control, almost a perfect control over the nanoribbon sizes. Now, using this method, we were able to pattern the semiconductor nanoribbon in wafer scale. As you can see in the bottom left, those light blue color in the middle are the color of the indium oxide. And if you look at them from a different angle, you can see the rainbow color from the nanostructures. So we were able to pattern those structures over the whole centimeter scale with high uniformity. And those are some SEM image and also the element analysis of the indium oxide nanoribbons. Now, with this fabrication technique, we were able to have those highly aligned and highly controllable nanowire transistors. Here we have the source and drain electrode. In between them are those patterned indium oxide nanoribbon or nanowires. And in between each pair of the electrode, there are around 1,850 wires between them. And also the number and the spacing can both be controlled preciously using the different stems. And those source string electrodes are shown here were patterned actually by conventional photolithography. You can see those zigzags from the conventional photolithography compared with the precious control achieved by chemical lithography in those indium oxide nanoribbon area. We then compared the sensitivity of different widths of nanoribbons. It is suggested that the surface volume ratio is critical for sensitivity of biosensors. For the same thickness, narrow nanoribbon have higher surface volume ratios, thus leading to a higher sensitivity. We investigated the sensitivity at a different pH, aptamer sensing, and also DNA sequencing. The results showed that transistor with 350 nanometer wide nanoribbons have higher sensitivity than the 20 micron meter wide ribbons, and which confirmed our hypothesis that devices with higher surface volume ratio have higher sensitivity. For our aptamer sensor shown here, we already added the physiological ranges, but for many other applications, such as the DNA sequencing, The lower detection limits means that we can detect the biomarker at an earlier stage without using the amplification such as PCR. This is even more critical under the current COVID-19 situation, which hopefully will be gone very soon. And if we were able to detect the virus RNA with a lower copy number, we'll be able to have a more accurate detection and hopefully earlier detection without the cost of amplification. To give you some taste on how those transistor biosensors are really useful in biomedical applications, this is one area that I have been focusing on during my PhD. We have been working on developing highly sensitive implantable aptamer biosensors that can monitor neurotransmitters in the brain. The ability to monitor neurotransmitters in the brain will provide a better understanding of the brain and also the neurological diseases. Those understanding will help researchers design better treatments and prevention strategies for brain disorders. I hope I will be able to share more of those in the separate talks in the future. I think those are also quite exciting results. To summarize, we have shown that we can use the CL to pattern different features such as lines, ribbons, disc arrays, and whole arrays of different materials, including metals and semiconductors. Moreover, the patterning can be achieved on a variety of substrates, including silicon, glass, or even polyimide, as what Rajesh just mentioned at the beginning of his talk. And I just saw another opportunity for collaboration. And we can even pattern those substrates on those nanostructures on just the petri dish. Due to the time limit, I cannot go detail for each of them, but you can check out those key papers out. And I'm more than happy to discuss with them in the Q&A session later as well. But there's one thing that I want to highlight here is that the software lithography enables more great biomedical applications from patterning to sensing. And recently we published this work for intracellular delivery. And we were able to pattern those nanostructure directly on the petri dish, and this enables in situ drug delivery upon the laser irradiation. Those will create some bubbles and for the delivery of some drugs into the cells. And this one was the 2020 ACS materials letters paper if you are interested to check those out. Now with all of this, I hope I have convinced you that chemical lithography has been shown to be a very strong, powerful tool for nanofabrication in biomedicine with its advantages as low cost, large area, and high throughput. I think those are quite exciting opportunities. Here, I would like to thank my PhD advisors, Professor Paul Weiss and Professor Andrews, as all the work I've done during my PhD at UCLA. I would also like to thank my current advisor, Professor Jenna Mao at Stanford. I would like to also thank our collaborators and funding agencies. Last but not the least, I would like to thank the organizer for organizing this great online event. I would like to thank Dr. Michelle for the invitation, and thank you all for your attention, and I'm happy to take any questions you have.
Thank you very much for the very inspiring talk. I really liked the ideas and the let's say, the creative solutions you came up with to enable low-cost nanofabrication.
Thank you.
Do we have questions? Tatif, you have a question.
Yes, thanks a lot. And in fact, just following up the idea of Natalia, I wanted to ask whether you can share with us with some small details on how to make that mask on the disc, because it's something very creative and very seems to be easy, but I don't think it's that straightforward. Could you please comment on that a bit more?
Absolutely.
If it's not a secret.
It's definitely not. It's all published. So let me find that slides, so it'll be easier. Okay. So actually, in this process, it's surprisingly, I mean, this, if you're interested, you can check out this paper as well. I have details in the, experimental session. But actually, they are, those are kind of, if you grab the whole CD and you just, cut them using some scissor, and you can see there are cut 2 layers, separate them up. If you just put a razor blade there, you can separate them. I mean, you have to be careful for sure because you don't want to break them. But you just put the razor blade there and you can separate those 2 layers very nicely, and the top layer and the bottom layer. And for the bottom layer is actually just 3 and 4. So the 3 is a die layer for the reading. If you need a movie, and those die can have a dot lines like 1, 0. Those are for the reading. And those 4 layer is just the the arrays for the circuits. But if you take a centimeter scale, those are just nanoscale features, can use them as lines. So, and if you take the substrate and you just rinse them with ethanol, and you basically get this, this is kind of large scale and over centimeter, a couple centimeter scale of the substrate. And this can be easily, if you just put PDMS and kill them, and if you peel them afterwards, you can get this, if you can see those, rainbow color here as well. So those are actually straightforward. And, there's surprising that not people are really using it, but, I definitely suggest you to give a try. And, shoot me an email if you found it's tough for you, and I'm more than happy to provide more guidance.
I'm going to try it.
Nice.
And
so one should just
yes.
One should just cut out all this stuff and look in the microscope. I think this is a takeaway message here.
And
also we have a different. Oh, go ahead.
Yeah, I'm wondering, how come did you came up with this idea?
This
it
was
seems
actually
so trivial, but it's not.
Yeah, one time I was looking for some decoration. The whole process was actually some blogger on the internet who tried to decorate your home, and she showed how to separate them, how to decorate your house with different used CDs. And those was actually very interesting, and I looked into them and found that you can actually use this for nanoscale features. Because I look at why there are 4 layers, and they show those 4 layers, and at the bottom they show some nanoscale features. Maybe I can use those. So the thing that then I tried actually is quite straightforward to make them. But originally some bloggers using them to decorate your home using some DIY process. But yeah, that's kind of where the inspiration I got.
I think this is insane. This is really awesome.
Genius. I have also another question. So I think it was the next slide of yours when you were showing that before lifting off and after lifting off, there was the difference.
Oh, okay. The nano ribbon. Here, right?
Yeah, here. So the difference, which is almost the half, could you please comment on that? Is it okay to have this 2 times difference between and after lifting off, or it's normal that you expected that?
Okay, so actually, the size is not even at the beginning, and this is due to when I put the PDMS to the CD. That's you have a very good eye to catch them, and the size of the pitch is set around 700, but the size is a little bit tiny here if you can fit in the PDMS stamps, and so that's why I took this AFM profile to match them and to see if they feel very, very well. So that's the thing of a little bit off, I would say, that when you put the PDMS into the mold, and if you take them off, and the size is gonna change a little bit. And that's something not from the patterning process, and because those can fit the one tiny one, a little bit larger one. This is more apparent here, but actually it's a kind of similar process, because I checked the profile. Actually, this dark one is a little bit narrow, and this yellow one is a little bit wide, and this become more apparent when I flip over the size. But that was not from the patterning, but more like a remolding process. We remove the PDMS from the CDs.
Okay, all right. Thanks a lot. I'm going to try with the disc. I will let you know the outcome.
Sounds great.
Thank you.
Any further questions from the audience or from the other panelists? Actually, I also had a question about the slide in the beginning where you showed the different devices that could enhance the human body.
Mm-hmm.
I wanted to ask, what do you think will be the first device that will really be used that way? What do you think is most feasible in the short term?
That's a great question. I mean, in the short term, it's definitely those wearable devices. I would say, me myself, I have Apple Watch. It's too early. I haven't put them on, but I have an Oura Ring that can track my heart rate variations. And they're not paying me anything, but this is not an advertisement. But I just put them on for my own health. Those devices, they can track the heart rate variations, or your body temperature, your daily life, and just for fitness, and Fitbit, as well. I think, this is when clothes is for the wearable, and I think there's and the Apple Watch can now do the blood oxygen level test as well. I think this is very close to the market that people can add different components or different new novel biosensors to those wearable devices, because those are non-invasive, and people will take with that because they are just watch on the waist. That's not a big deal. And I will say those minimal invasive or implantable devices, for example, the Neuralink that Elon Musk is working on. Those I think people may take some time to take them, or people will only take them if they have to, like if they really can bring some game changer to their whole life, then the people may put something really inside of their brain. But I think that might be a little bit further to the market at this point.
Yes, makes sense indeed. Okay, thank you. So if no further questions, let's
thank you.
I think there's another question
is there?
from Rajesh. Yes, yeah, because panelists cannot use Q&A. So
okay, please go ahead.
So Rajesh was asking if you have tried replication into 3D or 2.5D nanostructures.
A great question. I have not, yeah, but as I'm hoping to collaborating with you too on that. As I showed that, I don't have time to show in this slides, but let me pull out that slides at the end. That we were able to pattern those. Those is also in the I think 2 centimeter by 2 centimeter scale, and in the middle those are all nanostructures, and I can cut them smaller, put them on a bandage. And also this is can be wearable, and they are flexible as well. But yeah, I haven't got the time to play around with any 3D structure. That will be, I think, very cool and exciting as well. Yeah.
Great, thank you. Sounds good. Send me an email when you get a chance.
Sounds great. Will do.
Any last-minute questions? If not, thank you once again for the excellent talk. And so this brings us almost to the end of the conference, but our co-chair Tatev, she still has some important announcements to make, so please stick around for a couple of minutes more. Tatev, the floor is yours.
Thanks a lot. So I think you see my screen.
Yes.
So first of all, I would like to thank everyone who stayed with us until the end. It's very encouraging and very nice for all of us, the organizers of the first edition of Nanofabrication Photonics Online Meetup, to see all this enthusiasm and excitement. And this is really something that we expected and wanted to see. So during these 2.5 days, because we started the poster session still on Twitter on the 16th of May, we have had different sessions, multidisciplinary conference, including poster sessions, flash talks, image contests, career panels, networking, tutorial presentations, and of course today the whole day was technical presentations by our amazing invited speakers. We covered the whole world with all the participations and all the talks. So indeed, when we did some small statistics, like last second statistics before going to the presentation, because we have to still analyze all data. So happily to say that we had at this moment already counted 33 participant countries. So participants from all over the world joined the conference, and it's again amazing to see how nanofabrication can connect the whole world within 2 days. Then, of course, this everything wouldn't be possible if not our sponsors and partners. So big shout out to our sponsors, Heidelberg Instruments, Brussels Photonics, Genesis, NanofabNet, and our partners, International Day Flight and Photonics Online Meetup. They contributed with whatever we needed, we asked during the organization, and we are very thankful for their contributions, their help, their support. Saying so, I just would like to mention specifically each of them, their contribution, and one, I think this kind of initiative you cannot see in all the conferences, but here we have, thanks to Heidelberg Instruments, we will be able to donate 10 euros per participant who was present in GatherTown, poster sessions, networking sessions, and during the Zoom sessions. We will donate 10 euros per participant to Worldwide Foundation to protect the environment. The next very important message and very important competition, let's say, was announced still in March about the best poster prize, and after that I think we had some exponential increasing the numbers of abstracts, submitted abstracts, and thanks NanofabNet, who will provide with our prize, which is the noise cancelling headphones. I think every one of us would be really happy to have them. So just quick statistics again, we had 30 abstracts submitted, and note that this is one unique nanofabrication topic. So this is again very encouraging to see how people, and especially young researchers, they are interested in sharing the technical part of their work. And we had 50%, let's say, the participation in social media sessions. And of course, we had the winner, and we are very happy to announce our winner for the best poster prize, Preksha Tiwari, with her work on monolithical integration of indium gallium arsenium microdiscs on silicon for nanophotonic applications. Congratulations, Preksha, and I would like again to thank her for her very active participation and asking questions all these 2 days. It's very important to be open for discussions. Congratulations again, and we will contact you later on to arrange the prize delivery. Next, so as you also know, we had other prizes sponsored by Genesis, Heidelberg Instruments, and International Day of Light. So we have organized image contests, and the goal was to share with us the microscopic images of nanofabricated devices. Prize will be, special prize for Genesis will be the Picturing Science and Engineering book for our 3 winners. Within 33 images submitted. I don't know if it's a coincidence or not, but we had 33 countries participating and 33 images submitted. So it's again another nice coincidence, let's say. And moreover, our winners will be participating in events organized by Heidelberg Instruments in Germany or in Switzerland, depending on the pandemic situation. Again, next, Anya will share with you with the details later on. Oh, sorry, let me lower my hand. And finally, let me introduce you our winners. So we have 3 winners. First winner is Koen van Mol from Vrije Universiteit Brussels Photonics. And he submitted images that actually were included today during one of the invited talks. So congratulations, Koen, for this very nice work and submitted image. So he also provided a description, scanning electron microscope image of microstructured optical fiber tapers fabricated via 2-photon polymerization-based direct laser writing. And from left, he showed down taper, right up taper, and then he has the cross sections. Congratulations again. So the book is yours, and one of the books is yours, and the rest will be communicated later. The next winner is another very beautiful image from Laura Mercade Morales from Nanophotonics Technology Center, Universitat Politécnica de Valencia. And she presented a pattern silicon nanobridge. Again, amazing, very beautiful image. Congratulations her again. And a second book is hers. And finally, our last winner is Kaustubh Vyas from University of Ottawa. And the picture, the image is called plasma etching art. So it's really beautiful and it's art, let's say. So we congratulate all our winners. And again, delivery and everything will be communicated later on. So be patient and wait for your prizes. Thanks our sponsors for these beautiful prizes. And moreover, the winning images will be advertised by the International Day of Light social media, as well as ours, of course. Wait a second. Next, we will be answering to the question, what will be available soon? So I guess you are waiting to see our abstracts. So there will be abstract book coming soon. After the conference, we will include all the winner images, all the details, all a bit information, and very soon it will be available. And also another question which was asked, I think this question was asked more than anything else, whether the videos will be recorded and shared later on. Yes, we have done a recording, and later on, I don't know today, tomorrow, the day after tomorrow, but very soon they will be available. Just stay tuned, follow our social media channels, and you will definitely receive information. So then we would like also to share with some information about upcoming events. The first one, so since Heidelberg Instruments was also the sponsor partner of this event, I would like to share the upcoming events organized by them in October. So grayscale micro and nano direct writing lithography. The details will be soon available. And I think Anya will also that part communicate later on once the details are available. And of course, so POM, Photonics Online Meetup, which has its branches as our POM. There is another one, Belgian Photonics Online Meetup. So we invite everyone, especially our Belgian colleagues, to take part in the second edition of Belgian Photonics Online Meetup. Dates are from 23rd and 24th of September 2021. And again, more details will be available soon. I will communicate later on this. So saying this, I would like to thank again everyone. Thanks a lot for staying with us. Thanks a lot for giving us the positive vibe that we expected. And see you next time.
Just one thing before we say bye. I have posted the link for collecting feedback. So if you want to tell us what you think about the conference and how we can do better, please do fill in the questionnaire, and we'll also copy this link in the follow-up email. So if you don't want to do that now, that's fine. Just check your inbox.
Thanks a lot. So I guess this was all from our side. And I again would like to thank all the organizers, my co-chairs, participants, especially contributors, speakers for this amazing event. And yes, see you next time then. Bye.
So
Bye.
do we go
See you
to
next time?
Yeah, so we go to Gather Town if someone wants to hang out. There is time, and we can, yeah.
We have drinks.
Yeah, we can have drinks, exactly.
Thank you.
Exactly. So see you there, and thank you very much.
Bye.